Hello there, and welcome to Physics with William, where curiosity slows to a gentler pace, and even the most stubborn corners of physics are invited to sit down, loosen their tie, and explain themselves properly. Tonight we are turning our attention to something very small, very familiar, and far stranger than it has any right to be. We're going to talk about what a hadron really is, and in particular about the hidden particles inside protons, those quiet little residents of the atomic nucleus that most of us met in school and were then encouraged to treat as if the matter were settled. A proton, we were told, is a particle, nice and tidy, a neat little unit, case closed, and yet, as often happens in physics, the closer we looked, the less tidy the story became. Before we wander too far into that hidden interior, I would love to know where in the world you are listening from tonight and what sort of hour it is in your corner of the planet. Are you hearing this while the house has finally gone quiet, while the city outside is still humming, or while the morning is just beginning to gather itself together? There is something fitting about that, I think. A conversation about the inside of matter arriving in so many different rooms at so many different moments, while each of us sits beside a cup of tea or under a blanket, or pretending quite sincerely that we are absolutely about to sleep and not about to spend a suspicious amount of time thinking about subatomic particles. And if this little journey turns out to be soothing or interesting, or simply a pleasant way to let the mind drift while learning something unusual, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this calm little corner of science find other listeners who may also want to slow away into difficult ideas. I cannot promise that protons will become less complicated by the end of the evening, but I can promise that they will become better company. Now, at first glance, the proton does not look like a likely source of mystery. It has a respectable reputation. It is stable, dependable, easy to name, and it sits at the centre of ordinary matter with the quiet confidence of something that believes its paperwork is in order. Your body contains protons. Your walls contain protons. The stars contain protons. If the proton were a person at a dinner party, it would probably be the guest everyone assumes is straightforward, reliable, solid, possibly a bit dull. And then, sometime after dessert, someone would discover that it has 3 passports, 7 aliases, and an impossible living arrangement involving quarks and gluons that no one can fully describe without drawing diagrams on the tablecloth. That, more or less, is where our story lives. Because a hadron, despite the sturdy sound of the word, is not a single indivisible little bead of existence. A hadron is a composite particle, is built from smaller constituents held together by one of nature's fundamental forces. Protons are hadrons, neutrons are hadrons. They are not the end of the line. They are crowded places. They are busy on the inside. And although we often speak of them as objects, the closer physics gets to their interior, the less they resemble tiny billiard balls, and the more they resemble a restless system of motion, exchange, pressure, and constant activity. It is one of the most surprising habits of science that the familiar things are often the strangest once you stop taking them for granted. The proton feels ordinary because it has been near us all our lives. It's part of the furniture of reality. But familiarity is not the same as simplicity. A brick looks simple until you study the chemistry that made it. Water looks simple until you understand molecular bonds. The night sky looks simple until someone points out that those quiet lights are thermonuclear furnaces scattered across impossible distances. In much the same way, the proton seems simple until you ask the rude but necessary question: what exactly is inside it? And that question is worth asking gently, because it has a habit of opening more doors than expected. When many people first hear that protons contain smaller particles, the immediate response is reasonable. Fine, they say, what is inside the proton? 3 smaller things. Yes, quarks. Excellent. We have successfully shrunk the problem, we are done here. But this is physics, and physics does not usually reward optimism of that kind. Yes, the proton is often introduced as a combination of 3 quarks, That statement is useful. It is not wrong. It is also, in a very important sense, not the whole truth. Saying a proton is just 3 quarks is a bit like saying a city is just 3 roads, because those are the first ones you noticed on a map. Technically, something useful has been said. Practically, the situation remains far more crowded. Inside the proton there are quarks, certainly, but there are also gluons, the particles that carry the strong force and bind quarks together. And there is more. There is a kind of ceaseless internal activity in which particles appear, interact, exchange momentum, and vanish again in ways that make the proton less like a little container of fixed objects, and more like a dynamic structure whose identity is maintained through motion and interaction. It is stable as a whole, but lively within. Calm from a distance, unruly up close. Rather like a duck on a pond, if ducks were composed of quarks and governed by quantum chromodynamics. Now, that last phrase may sound as though someone in a laboratory lost a bet with the naming committee, but it matters. Quantum chromodynamics is the theory that describes the strong interaction, the force responsible for binding quarks into hadrons, and strong in this case is not an exaggeration. Without it, protons would not exist in any recognizable way, atomic nuclei would not hold together, and the entire material world would have serious structural concerns. The strong interaction is not a minor supporting character in the drama of matter. It is the reason the stage is still standing. Still, before we get too technical too soon, it helps to slow down and notice just how odd the idea of a hadron really is. We live our daily lives surrounded by objects that seem solid, still, and complete. A table sits where you left it. A stone remains a stone. A book rests on a shelf without visibly trembling from internal crisis. Even when we remember that matter is made of atoms, and atoms contain nuclei, and nuclei contain protons and neutrons, there is often still a lingering intuition that somewhere near the bottom of things there must be little solid units holding the line, tiny nuggets of certainty, small pieces of matter that are simply there. But nature, rather annoyingly and magnificently, does not seem especially committed to giving us that kind of comfort. The deeper we go, the less the world looks like a stack of miniature objects, one tucked neatly inside another. Instead, it begins to look like patterns of behavior, stable arrangements of energy, and relationships governed by laws that are mathematically precise and conceptually uncooperative. A hadron is real, certainly. It has measurable properties. It can be detected, studied, accelerated, and smashed into other things at alarming speeds by very dedicated people. But it is not simple in the old intuitive sense. It is not a tiny rock. It is a bound state. It is a structure held together by interaction. Its insides are not arranged like parts in a watch. They are more active, more fluid, and more difficult to picture honestly. That gap between what we want matter to be and what it actually is has shaped much of modern physics. Again and again, the universe has shown an almost playful tendency to refuse our first picture of it. We say atom, meaning indivisible, and discover that atoms have internal structure. We say nucleus, imagining a compact centre, and discover that its components are themselves composite. We say proton, thinking perhaps we have finally arrived at a reasonably respectable endpoint, and the proton says, not so fast. There is also something very human in the way we react to this. We like layers, provided there are not too many of them. We enjoy a reveal, provided it does not lead to another reveal, and then another, and then a graduate degree. We like to know what things are made of, what things are. Wood is made of fibres, steel is made of crystals, molecules are made of atoms. Good, excellent progress. But once we reach the world of hadrons, our ordinary habits of explanation begin to strain. Because what a hadron is made of cannot be told as a simple inventory alone. It must also be told as a story about force, confinement, exchange, motion, and the peculiar rules of the quantum world. Even the word particle becomes a little slippery here. In everyday speech, a particle sounds like a tiny speck, a grain, a dot too small to see but otherwise familiar in spirit. Dust is particulate, sand is particulate. Sprinkle enough science on top and one imagines smaller, fancier dust. But in modern physics, particles are not always small, hard lumps. They're excitations, entities with quantized properties, things that can behave in ways no grain of sand ever would. And when they bind together into composite systems like hadrons, their reality becomes inseparable from the interactions holding them together. So when we ask what a hadron really is, we're not merely asking for a list of ingredients. We're asking what kind of thing it is in the first place. Is it a container of smaller parts? Is it a system of forces? Is it a pattern that persists through internal motion? The answer, unhelpfully but truthfully, is that it is some mixture of all of those, an understanding that mixture took decades of experimental work, theoretical struggle, and a willingness to let go of older pictures of matter. There is another reason this topic deserves patience. The proton is not obscure, it is central. If we were discussing some exotic particle glimpsed once in a detector, before disappearing behind a very expensive graph, that would be one thing. But the proton is one of the main ingredients of visible matter. If something as common as a proton turns out to be internally rich and conceptually difficult, then the lesson is not just about protons. The lesson is that the everyday world is built on structures far more subtle than everyday experience suggests, and that can be oddly comforting in its way. The ordinary world is not less wonderful because we explain it. It becomes more wonderful because the explanation deepens it. A wooden table remains a table, but it is also chemistry, electromagnetism, molecular structure, atomic arrangement, nuclear binding, and subatomic dynamics all the way down. A proton remains the quiet little particle from schoolbook diagrams, but it is also a crowded quantum object bound by the strongest force in nature, containing within itself a complexity that took some of the smartest people on Earth a very long time to begin describing properly. It is worth lingering on that for a moment. People did not discover this all at once. No one woke up one morning, glanced at a proton and said, "Ah yes, clearly a hadron with internal quark structure and gluon dynamics." The history was messier. Physics had to be pushed. Experiments had to become clever enough to probe deeper. Theories had to survive contact with reality. There were hints, contradictions, partial models, and long stretches in which the data seemed to be waving at a truth no one could yet state cleanly. The proton did not surrender its inner life willingly. Scientists had to interrogate it with scattering experiments, accelerators, detectors, and more patience than most of us can muster while waiting for the kettle. And perhaps that is part of the reason the subject still feels alive. A hadron is not just a concept in a textbook. It is a place where our understanding of nature had to be rebuilt. It marks the point where the apparent solidity of matter gave way to an unexpectedly active inner world. It reminds us that stability on the outside can conceal turmoil within, which is true of many things besides subatomic particles, though thankfully most tables do not require a theory of the strong interaction to remain emotionally coherent. Now, since we are beginning at the beginning, there is a temptation to rush forward and name all the inner residents at once. Quarks, gluons, valence quarks, C-quarks, confinement, color charge, deep inelastic scattering. And we will get to all of that, but it helps first to plant our feet on the basic ground. A hadron is a particle made of quarks held together by gluons through the strong interaction. That is the essential definition. Protons and neutrons are the best known examples. They belong to a family called baryons, which are hadrons built in one particular way. There is another family called mesons, made from a quark and an antiquark. Different arrangements, same underlying force. The hadron, then, is not a basic indivisible point in the old classical sense. It is a bound structure. That word bound matters more than it may seem. A bound structure is not merely a pile. It is not an accidental heap of ingredients. It is a stable system because the interactions among its constituents hold it together in a definite way. If the force vanished, the hadron would not continue politely as a loose collection of spare parts. Its very identity depends on the binding. In that sense, the hadron is as much about the force as about the particles involved. Remove the strong interaction, and the hadron ceases to be what it is. This is one of the strange but important shifts in modern physics. We stop thinking only in terms of objects and begin thinking in terms of relationships that define objects. The proton is not merely three quarks that happen to sit near one another. It is a tightly bound quantum state sustained by the exchange of gluons and shaped by the rules of the strong force. Its properties, such as mass and spin, do not emerge from a simple addition of little pieces in the way one might add apples to a basket. They arise from the whole system, and that means that to understand the proton, we must understand not only what is inside it, but how the inside behaves. Which brings us quite naturally to the part where old ideas began to fail. Because there was a time when many physicists hoped the particle story would become simpler as it went on. First atoms, then electrons and nuclei, then protons and neutrons, then perhaps the final set of basic particles, each with a few clear properties and a reassuring lack of surprises. What actually happened was more like opening a wardrobe and discovering not Narnia exactly, but a large and increasingly crowded particle zoo. New entities kept turning up, patterns appeared, families formed. Some particles seemed fundamental, others composite, and the tidy border between those categories had to be fought for experimentally. By the middle of the 20th century, it was becoming harder to pretend that protons and neutrons were featureless little marbles. Evidence was accumulating that they had size, structure, and internal organization of some kind. The details were not yet settled, but the neatest picture of matter was beginning to wobble. And once scientists started probing these particles with higher energies and sharper methods, the wobble became impossible to ignore. The proton was not empty, not simple, and not final. That is where the next stretch of the story takes us. Because before we can properly understand what a hadron really is, we have to spend a little time with the moment physics stopped treating particles like perfectly solid things and started discovering that even the apparently basic pieces of matter could have an internal life of their own. That change did not happen all at once, and it certainly did not happen because anyone was eager to make matter more complicated than it already was. For quite a long time, the dream in physics was almost the opposite. The hope was that if you kept peeling reality back layer by layer, the world would eventually present you with a set of clean, hard, final ingredients. Little units that simply were what they were. Solid, distinct, reliable. The kind of components you could put in a neat list and then go home feeling that the universe, while perhaps large and occasionally dramatic, was at least decently organized. That instinct made perfect sense. Most of our everyday experience points in that direction. A pebble is a pebble, a grain of sand is a grain of sand. Break something apart and it becomes smaller pieces of the same kind of thing. Chop wood and you get splinters. Crush rock and you get dust. Even when we cannot see the tinier scale directly, the mind wants to imagine it as more of the same. Smaller bits, finer crumbs, matter reduced until it reaches its final grain. That was the spirit behind some of the earliest atomic ideas. Long before modern laboratories, ancient thinkers had already guessed that matter might be made of indivisible units. The very word atom came from the notion of something that could not be cut any further. It was a powerful idea, and in many ways a brilliant one. Matter really does come in discrete building blocks. But as history would show, the part about indivisibility was a little too optimistic. Nature, it turns out, is quite happy to hand us a useful concept, and then wait calmly while we overestimate how complete it is. By the 19th century, atoms had become more than philosophy. Chemistry had given them real weight. Scientists could infer their existence from the regular behavior of elements and compounds. Matter was not just continuous substance, after all. It had structure. It was made of atoms, and atoms explained why substances combined in fixed proportions and behaved in repeatable ways. This was a triumph. It felt like progress of the best kind. Simple, elegant, satisfying. The atom seemed to be the long-awaited answer, the firm little bead at the base of material reality. And then, naturally, the atom turned out to have internal parts. That was one of the first great shocks in the modern story of matter. Not because scientists hated surprises, though I suspect some of them would have appreciated fewer of them before lunch, but because it changed the whole tone of the investigation. If the atom itself could be broken open conceptually, then nothing above it in the hierarchy could be trusted to be final. The old hope of reaching tiny solid units began to weaken. The world was not giving us polished marbles. It was giving us layers. The electron was one of the first clues. When experiments with electric discharge tubes revealed something smaller than the atom, something carrying a definite electric charge, the old image of the atom as indivisible had to be abandoned. The atom still existed, still mattered, still explained chemistry, but it was no longer fundamental in the old sense. It had become a structure, a system, a thing with parts. Even then, however, the imagination tried to preserve solidity where it could. Early models of the atom treated it as a kind of little mechanical arrangement. There were attempts to picture electrons embedded in positive matter, or orbiting in miniature solar systems, or arranged in ways that still felt concrete and object-like. This is one of the recurring patterns in physics. We do not surrender familiar imagery easily. When confronted with something new, we first try to fit it into shapes the mind already knows. Then came the nucleus, and with it, another collapse of simplicity. The famous scattering experiment showed that the positive charge of the atom was concentrated in a tiny central region. Most of the atom was empty space. That alone was startling enough. Matter did not resemble a tiny solid bead at all. It resembled a mostly empty structure with dense centres and lightweight inhabitants. Already the word solid had begun to wobble. A table feels solid to your hand, but the atoms inside it are mostly space, and their rigidity comes not from little packed pebbles but from electromagnetic interactions and quantum rules that prevent matter from simply sinking through itself. Even before we reach the proton, solidity is starting to look less like a property of stuff and more like a consequence of forces and structure. That is an uncomfortable idea at first. We like the sensation that solid things are solid because they are made of solid material all the way down. But physics is less sentimental. It tells us that what we experience as hardness or resistance often comes from interactions, not from miniature versions of macroscopic firmness. The chair beneath you is not solid because it is built from tiny chairs. It is solid because the particles and fields within it interact in ways that produce stability and resistance at human scale, which is less intuitive, admittedly, but considerably more accurate. Once the nucleus was recognised, one might have hoped the story would settle for a while. Fine then. Atoms are not final, but nuclei might be. Tiny, dense, respectable things. Surely those are the proper building blocks. Yet the nucleus also turned out to contain structure. Protons and neutrons emerged as its main constituents, and for a time they looked like promising candidates for that long-desired category of basic matter. They were small, massive compared with electrons, and central to the architecture of ordinary stuff. If one were betting on where nature might finally stop being clever, this would not have seemed an unreasonable place to put money. But even as that picture took hold, something more profound was happening beneath it. The entire concept of what a particle was had begun to change, not just because new particles were being discovered, but because quantum theory was rewriting the rules for how physical things behaved. The old image of a particle as a tiny billiard ball with a perfectly definite path through space was becoming harder to defend. Electrons did not behave like little pellets in any simple classical sense. Light did not behave like a smooth wave in any simple classical sense either. Both seemed to cross categories in ways that embarrassed neat mental pictures. Wave-like behaviour and particle-like behaviour were turning up in the same entities. Matter could interfere with itself. Tiny objects could not always be assigned definite positions and motions the way ordinary objects could. Observation itself entered the story in strange ways. The world at small scales was not merely hidden from direct view. It behaved differently from the machinery of common sense. This mattered for our subject more than it may seem. Because once particles stopped being little classical pellets, the possibility opened that even those things we still called particles might be less object-like than their name suggested. A proton could still be real, still measurable, still a particle in the language of the laboratory, while no longer fitting the old picture of a tiny hard speck. And as evidence accumulated, that is exactly what began to happen. There is a habit in science education of presenting discoveries as if each new fact simply replaced the previous one in an orderly line. First people thought this, then they discovered that, then all sensible parties agreed and moved on. Real history is much less tidy. Older pictures linger because they are useful within certain limits. Atoms are still real, nuclei are still real, protons are still real. The problem is not that earlier scientists were foolish to describe them as particles. The problem is that the word particle quietly changed under pressure from experiment. A particle in modern physics is not necessarily a tiny solid object with a sharp edge and a miniature surface. It is an entity with quantized properties, something that can be created, detected, exchanged and classified, but not always visualized honestly in everyday terms. Sometimes it behaves in a localized way. Sometimes it spreads its influence like a wave. Sometimes its properties only make full sense within a deeper theoretical framework built from fields and symmetries. The word stayed. The intuition had to be rebuilt. This shift became especially important in the middle of the 20th century, when physicists began studying subatomic collisions with growing energy and precision. Higher energy probes acted like sharper questions. If you want to know whether something has an internal structure, one effective method is to strike it with something energetic enough to reveal hidden detail. Not because scientists are violent by temperament, though particle accelerators do suggest a certain willingness to solve mysteries by dramatic means, but because scattering experiments are among the best tools we have for probing what cannot be seen directly. That method had already transformed the atom. By observing how particles scattered from thin foils and other targets, scientists could infer the existence of nuclei and the distribution of charge. Later, similar logic would be applied to protons and neutrons. If these were truly elementary, truly featureless, then probes sent into them should respond in one way. If they contained smaller constituents or internal patterns, the scattering would reveal something else. And that is exactly where the old notion of solidity began to fail in a deeper sense. The proton did not behave like a simple, structureless bead. Under sufficiently energetic scrutiny, it began to show signs that there was more inside. The details took time to sort out, but the message was unmistakable. What had once seemed like one of the final pieces of matter was itself composite or at least internally organized in some profound way. Before those results became clear, however, there was already mounting trouble from another direction. Physicists were discovering more and more particles, not just electrons, protons and neutrons, but a growing menagerie of unstable short-lived entities produced in cosmic rays and accelerator experiments. Some lasted only briefly, some carried strange properties, some appeared in families and patterns that hinted at underlying structure. The world of the small was no longer a sparse set of simple ingredients. It was becoming crowded. This crowding had an odd effect on scientific intuition. On the one hand, it made the particle world look messy, almost too full to be fundamental. On the other hand, it encouraged the suspicion that many of these particles might not be elementary after all. Chemistry had once found order in the many substances of the world by recognizing them as combinations of a smaller set of elements. Perhaps particle physics needed a similar reorganization. Perhaps the apparent zoo concealed a deeper simplicity. That suspicion did not arise from theory alone. Experimental behavior kept nudging physics away from the idea of tiny solid units and toward the idea of structured systems. Some particles came in groups with related properties. Some decayed into others in patterns that suggested internal rules. Some could be understood more naturally as combinations rather than indivisible individuals. It was becoming harder to believe that every named particle was a final constituent of reality. At the same time, quantum field theory was teaching an even more unsettling lesson. What we call particles may be better understood as excitations of underlying fields rather than as independent little objects moving through empty space like grains in a void. The field picture is not especially friendly to everyday imagination, but it is powerful. In that view, the basic ingredients of nature are not tiny marbles but fields spread through space, and particles are localized manifestations of those fields. Already you can feel the old idea of solidity slipping away entirely. If the foundations of matter are field excitations, then the language of little hard bits becomes more metaphor than mechanism. Still, ordinary language is stubborn, and with good reason. We continue to say particle because the entities we study do leave point-like tracks in detectors, arrive in countable numbers, and transfer energy in discrete chunks. The language remains useful. But usefulness should not be mistaken for a complete mental picture. By the time physicists began seriously questioning the internal structure of the proton, the idea of a particle had already been softened by decades of quantum evidence. So when solid particles stopped being solid, the change was not merely about discovering smaller things inside larger things. It was also about losing the old classical image of matter as miniature hardware. The atom was not a bead. The electron was not a tiny planet. The nucleus was not a hard little pebble. And the proton, when the moment came, was not a final nugget either. Each stage of investigation replaced apparent solidity with structure, and then replaced simple structure with stranger forms of organization. There is something almost humbling in that progression. Every time physics thought it had reached a clean endpoint, reality replied with another layer. Yet the new layer was never chaos for its own sake. It came with patterns, laws, and deeper coherence. The world did not become less intelligible. It became intelligible in a more demanding way. The reward for giving up the comfort of solid little particles was a far richer account of how matter actually works. One of the most important examples of this came from deep scattering experiments in the later 20th century. By firing high-energy electrons at protons, physicists could examine how the proton responded under close scrutiny. What emerged was startling. The proton behaved as though it contained smaller point-like constituents inside it. Not a smooth blob, not a single rigid object. Something lumpy in a very precise sense, though lumpy is not, I should stress, the approved technical term. Those inner constituents would come to be understood as quarks, and the theory surrounding them would explain why they never appear alone in ordinary conditions. That result did more than add detail to the proton. It completed a long shift in how matter itself was imagined. The proton, once a candidate for final solidity, had become another place where reality was dynamic, relational, and internally active. Even worse for anyone fond of tidy pictures, the proton was not just three little objects sitting quietly together. It was a bound quantum system with internal motion, force-carrying gluons, and a fluctuating sea of additional activity. The closer physicists looked, the less the proton resembled a tiny stone, and the more it resembled a bustling, tightly held arrangement whose stability emerged from continual interaction. This is why the old word solid becomes so misleading at small scales. Solidity, in the everyday sense, suggests immobility, completeness, and a clear boundary between inside and outside. Hadrons do not fit that image well. They are stable, yes, but not still. They are real, yes, but not simple. Their identities are not those of miniature pebbles. They are maintained by the strongest force in nature, and much of what they are depends on the energy and motion within them. Even mass, which we often treat as the most straightforward property of matter, becomes more subtle here. The mass of a proton is not just the direct sum of the bare masses of its constituent quarks in any naive sense. Much of it arises from the energy of the strong interaction itself, from motion and binding and the restless internal structure of the system. So even the heft of ordinary matter, the thing that makes the world feel substantial, is tied not simply to little massive parts, but to dynamic relationships inside hadrons. The proton is heavy not because it contains 3 tiny cannonballs, but because the energy of its internal life contributes overwhelmingly to what we measure as mass. At that point, the old picture is not merely cracked, it has given way entirely. Matter is not built from final hard grains. It is built from layers of structure, from fields, from bound states, from interactions that generate the properties we once attributed to miniature solid pieces. The world still holds together. Your chair remains commendably committed to being a chair, but the reason it does so is much more interesting than a stack of tiny rigid pellets. And perhaps that is the main lesson of this part of the story. Physics did not lose reality when particles stopped being solid. It gained a better one, a more difficult one, yes, less friendly to the imagination at first glance, but also more honest. The universe turned out not to be a warehouse of little stones. It turned out to be a hierarchy of organized systems whose apparent stability comes from deeper patterns of activity. That realization sets the stage for the question we really need to face now, because once the proton stopped looking like a final solid object, it became necessary to ask what kind of thing it actually was, and what exactly we mean when we call something like a proton a hadron. So once the proton stopped looking like a tiny solid endpoint, the obvious next question was what sort of thing it actually is. Not what it is called, because physics is full of names that sound reassuring long before they become clear, but what kind of object it is in the deepest useful sense. And that is where the word hadron begins to matter properly. A hadron is a particle made from quarks and held together by the strong interaction. That is the clean version. It is short, accurate, and only mildly intimidating. But as with many clean definitions in physics, it becomes much more interesting the moment you try to take it seriously. Because every part of that sentence matters. It matters that a hadron is made from smaller constituents. It matters that those constituents are quarks. And it matters very much that they are held together not by an ordinary glue in the everyday sense, but by the strongest binding force in nature, one that behaves very differently from the forces we meet in daily life. The first useful thing to say is that hadrons are not a minor side category. They are central to ordinary matter. Protons are hadrons. Neutrons are hadrons. If you are sitting in a chair, leaning against a wall, wrapped in a blanket, or holding a mug that has gone slightly cooler than you intended because physics videos do have that effect on tea, then you are surrounded by hadrons. Most of the visible mass in the world around you is built from them. So although the word can sound technical and slightly remote, hadrons are not distant curiosities. They are among the main structural pieces of the everyday universe. That can be easy to miss because the word proton arrived in school far earlier than the word hadron did for most people. Proton sounds familiar. Neutron sounds familiar. Hadron sounds like something that should either be in a collider or in an expensive Scandinavian kitchen catalogue. But the relationship is simple. Proton and neutron are specific members of the broader hadron family. Calling a proton a hadron is a little like calling an oak a tree. You are placing the object in its larger category, the category defined by its inner structure and the force that holds it together. There are 2 main families of hadrons. The first are baryons, and this is the family that includes protons and neutrons. The second are mesons. Both are made of quarks, but they are arranged differently. Baryons are built from 3 quarks. Mesons are built from 1 quark and 1 antiquark. Different compositions, same deeper principle. In both cases, what makes them hadrons is that quarks are bound together into a composite particle by the strong interaction. That is the unifying idea. Now, if all of that sounds pleasantly manageable so far, this is where it starts becoming slightly less cooperative. because when we say a hadron is made of quarks, it is tempting to picture something simple. 3 little pieces inside a proton, perhaps sitting in a tidy triangular arrangement like passengers who arrived early and chose sensible seats. Or in the case of a meson, a neat pair keeping one another company. But hadrons are not mechanical miniatures of that kind. They are quantum systems, and the way their constituents exist inside them is not as straightforward as the way ingredients sit in a recipe. A hadron is better thought of as a bound state than as a container full of parts. That phrase matters. A bound state is a stable quantum object whose identity depends on the interactions among its constituents. The hadron is not just quarks placed side by side. It is the total system formed by their ongoing relationship through the strong interaction. If that relationship vanished, the hadron would not remain a useful object in pieces. It would cease to be a hadron at all. This is one of the places where modern physics asks us to adjust our instincts. In everyday life, we're used to objects being more than the sum of their parts in a loose poetic sense. A cake is not just flour and eggs. A city is not just bricks and roads. Fair enough. But in particle physics, that statement becomes far more literal and technical. The properties of a hadron do not arise from a simple addition of the independent properties of quarks as if one were tallying groceries. The mass, spin, momentum distribution, and overall behaviour of the hadron come from the full internal dynamics of the bound system. The strong force is not a minor detail attaching otherwise complete pieces. It is part of what the hadron is. That is why it helps to be careful with the word inside. When we say there are quarks inside a proton, that is true, but it risks suggesting a neat separation between the contents and the thing containing them. A hadron is not like a box with marbles in it. The box itself is made by the binding. The structure is the interaction. The thing exists as a stable object because of the continual exchange and confinement of its constituents. So when we speak of what is inside a hadron, we are speaking about a dynamic internal state rather than a quiet inventory. There is another subtle point here that often surprises people the first time they hear it. A hadron has a definite identity, but its interior is not frozen. The proton remains a proton. Its charge is fixed. Its spin is fixed. Its overall nature is stable. Yet within that stability there is ongoing activity. Quarks carry momentum. Gluons are exchanged. Additional quark-antiquark pairs can briefly appear as part of the quantum behaviour of the system. The hadron is not unstable in the everyday sense, but it is far from still. Its stability is a managed stability, the kind that comes from strong internal rules rather than internal silence. If that sounds odd, it helps to compare it with more familiar kinds of stability. A spinning top can be stable because it is moving, not because it is motionless. A star can be stable for long periods because competing processes balance one another, not because nothing happens inside it. In a very different but related way, a hadron is stable because the strong interaction organises intense internal activity into a lasting bound state. It is a quiet object from the outside and a very busy place from within. This also explains why the discovery of hadrons was not just a matter of naming new particles. It was a shift in classification and understanding. Once physicists began noticing that protons, neutrons, and many other strongly interacting particles seemed related, it became necessary to group them according to deeper rules. The word hadron emerged as part of that effort. It allowed physicists to distinguish particles that feel the strong interaction in this composite way from those that do not. Electrons, for instance, are not hadrons. They are leptons. They do not contain quarks. They do not participate in the strong interaction in the same way. So the category is not random. It marks a real structural division in nature. That distinction matters because for a long time, the particle world looked crowded enough to be almost discouraging. New particles kept showing up in experiments. Some were stable enough to study well. Others decayed almost immediately. Some seemed related in mysterious patterns. It began to feel a bit like opening a supposedly well-organised cupboard and discovering 32 nearly identical containers with labels you do not quite trust. There had to be a deeper order somewhere. The concept of hadrons helped organise that mess by revealing that many of these particles were not elementary in the way once imagined. They belonged to a common structural class. Once that class was recognised, the next step was to understand what made hadrons behave the way they did, and that brought physics to the strong interaction, the force responsible for binding quarks together. This force is carried by particles called gluons, a name that at least has the courtesy to hint at what they do. But gluons are not just tiny bits of adhesive. They are the carriers of a very unusual force, one that behaves quite differently from electromagnetism. With electric charge, the force between charged particles becomes weaker as they move farther apart. With the strong interaction, the opposite tendency appears in an important sense. Quarks are easier to move relative to one another when they are extremely close together, but trying to pull them apart does not free them in the way common sense might expect. Instead, the force between them remains strong enough that separating them becomes enormously difficult. In ordinary conditions, quarks do not wander off by themselves. They remain confined inside hadrons. That feature is one of the defining facts of the whole subject. This is why hadrons are not merely optional gatherings of quarks. They are the form in which quarks are actually found in the world we observe. Free quarks, moving around alone like stray electrons, do not appear under normal circumstances. Quarks live in hadrons because the strong interaction confines them there. So to understand a hadron is to understand the natural state in which quarks show up when nature is left to its own devices. That confinement also helps explain why hadrons felt solidly individual for so long. We do not see quarks directly popping out of protons like loose pieces from a badly assembled cabinet. The proton appears as a stable particle because the quarks are permanently bound within it. Only by probing with high energies and interpreting scattering data carefully could physicists infer the inner structure. The hadron, in that sense, presents a unified face to the world, even though it is internally composite. There is something almost architectural about that. A building presents itself as one thing from the street, but it is a system of beams, walls, stresses, supports, and tensions. If the internal relationships vanished, the building would not continue as a pile of independent buildingness. It would stop being a building. A hadron is obviously not a building, and quarks are not contractors, though some of them do seem permanently overworked, but the principle is similar. Structure is not just about ingredients, it is about the force and arrangement that make a stable whole. This becomes even more important when we think about mass. Many people assume that the mass of a proton must mostly come from the masses of the three quarks usually associated with it. That sounds reasonable at first. Three things added together should make the total, but this turns out to be deeply misleading. The bare masses of those quarks account for only a small fraction of the proton's total mass. Most of the proton's mass comes from the energy associated with the strong interaction and the motion of its constituents. In other words, the proton weighs what it weighs, largely because of its internal dynamics. That is a remarkable fact, and it tells us something profound about hadrons. They are not just little storage cases for pre-existing mass. They are places where energy bound into a particular quantum system becomes most of the mass we observe. So when you lift an object, when matter resists acceleration, when ordinary stuff exhibits heft, much of what you are dealing with comes from the energetic internal life of hadrons. The familiar weight of the world owes an extraordinary amount to the hidden activity inside protons and neutrons. All of this means that calling a hadron a particle is correct but incomplete, unless one has updated what the word particle means. A hadron is not elementary. It is not indivisible. It is not static. It is a composite quantum object with stable observable properties, arising from a restless and strongly bound interior. It behaves as one particle in many experiments because the bound state is real and coherent. But that one particle is made possible by smaller constituents and the force that keeps them together. This is also why hadrons can come in many varieties. Once you allow quarks to combine under the rules of the strong interaction, multiple distinct bound states become possible. Some are stable enough to matter in ordinary matter, like the proton and neutron under the right conditions. Others are short-lived but very real, appearing in high-energy processes and then decaying into lighter particles. The hadron family includes a great many such states, some long known, some more exotic, and each one teaches physicists something about how quarks can be arranged and how the strong force behaves. At this point, it is useful to slow down and notice what has happened to our idea of matter. We started with the hope of final solid particles. Then atoms became structured, nuclei became structured, protons became structured, and now the hadron stands before us not as a disappointment but as a deeper category. It tells us that nature builds durable things not merely from tiny hard pieces, but from strongly bound systems whose internal relationships are essential to what they are. The hadron is not less real because it is composite. It is more informative. It shows us how real structure can emerge from intense interaction. There's also a curious elegance in the fact that the most familiar hadrons are so stable, while many of their relatives are not. Stability in physics is never just a matter of luck. It comes from rules, conservation laws, available decay pathways, and the energetic bookkeeping of the universe. The proton, for all its internal complexity, is astonishingly durable. Other hadrons exist only briefly before transforming into lighter products. This variety gives the hadron family a kind of layered personality. Some members are foundational furniture of ordinary matter. Others are fleeting but essential clues about the deeper theory. And that deeper theory, though we need not drown in its most technical language tonight, tells us that hadrons are the visible consequence of quark behaviour under the strong force. They are what the theory produces when quarks are confined. They are not awkward exceptions to a cleaner picture. They are the natural result of the rules themselves. In that sense, the hadron is not a compromise between simplicity and complexity. It is the honest form matter takes at this level. Even the distinction between baryons and mesons, simple as it sounds, hints at how systematic this is. Protons and neutrons are not random accidents. Mesons are not random accidents. They are allowed bound states within a well-defined framework. Some are more stable than others. Some are easier to produce or detect than others, but all belong to the same broad logic. Quarks do not float about freely. They organize into hadrons. That is why the question, what is a hadron, really becomes richer the longer you sit with it. It is a particle, yes, but one within a structure. It is a composite object, but one whose constituents cannot simply be pulled out and inspected like spare parts on a tray. It is stable, but internally active. It is ordinary enough to make up most of the mass around you, and strange enough that understanding it required one of the most sophisticated theories in all of physics. It sits right at the meeting point between the familiar world of matter and the deeply non-intuitive world of quantum forces, and once that much is clear, the next thing we have to face is the identity of the constituents themselves. Because it is one thing to say that hadrons are made of quarks, and another thing entirely to understand what quarks are, why there seem to be different kinds of them, and how those hidden building blocks manage to produce something as common and stubbornly substantial as a proton. So once physicists accepted that hadrons were not elementary after all, the next problem arrived immediately, and it was a rather serious one. If protons and neutrons were built from smaller ingredients, then what exactly were those ingredients, and why had no one ever seen them sitting on their own in the wild like respectable particles introducing themselves properly? This is where quarks enter the story, and they enter it in a way that is both elegant and faintly troublesome, which is usually how the best ideas in particle physics behave at first. A quark is an elementary particle, at least as far as our current understanding goes. It is one of the fundamental constituents used to build hadrons. Protons contain quarks. Neutrons contain quarks. Many other hadrons do as well. Quarks carry properties such as mass, electric charge, and spin, and they participate in the strong interaction, which is the crucial point for our purposes. That strong interaction is what binds them into hadrons and what prevents them from appearing as free particles under ordinary conditions. Now, the word elementary deserves a moment of care. In everyday speech, elementary sounds like simple, easy, almost introductory. In physics, it means something much more specific. It means not known to be built from smaller parts. An electron is elementary in this sense. A quark is elementary in this sense. A proton is not, because it is made of quarks. So when we call quarks the building blocks of hadrons, we are saying that at the level relevant to hadronic structure, quarks are the more basic constituents. That said, quarks do not behave like building blocks in the way bricks behave in a wall. Bricks remain bricks when you carry them around. They can be stacked, counted, weighed, and left in a wheelbarrow without the universe objecting. Quarks are not like that. They are more elusive. They are not found by themselves in normal circumstances. They are always bound into larger composite systems such as protons, neutrons, or other hadrons. So they are building blocks in a technical sense, but not in the friendly hardware store sense. The idea of quarks first emerged because the growing list of hadrons was becoming too complicated to ignore. Physicists were discovering more and more strongly interacting particles, and the pattern needed explanation. It began to look as though these particles might be combinations of a smaller set of more fundamental ingredients. That was the kind of move science had made before. Chemistry had found order in the apparent chaos of substances by tracing them back to elements. Perhaps particle physics could do something similar by tracing the hadron zoo back to a smaller set of constituents. That was the appeal of the quark model. It brought order to what had begun to look crowded and untidy. Suddenly, many hadrons could be understood as combinations of a small number of more basic objects. Protons and neutrons no longer had to be treated as unrelated little lumps. They could be described using quark content. Patterns that had seemed mysterious began to make more sense. Charges lined up. Groupings lined up. The zoo started looking less like a random collection, and more like a family tree with a few very eccentric cousins. In the simplest and most familiar cases, the proton is built from 2 up quarks and 1 down quark, while the neutron is built from 2 down quarks and 1 up quark. That sounds manageable, and it is a good place to begin. The up quark and the down quark are the lightest and most important quarks for ordinary matter. They are the ones that make up the protons and neutrons in atomic nuclei. If you stripped the visible world down to the quarks most responsible for its daily existence, those two would be doing most of the work. Their electric charges are unusual in a way that initially seems almost rude. We're used to charges coming in whole units when we think about familiar particles. The electron has 1 unit of negative charge in the usual convention. The proton has 1 unit of positive charge. Quarks, by contrast, carry fractional electric charges. An up quark carries a positive charge of 2/3 of the proton charge, while a down quark carries a negative charge of 1/3 of the proton charge. Put 2 up quarks and 1 down quark together, and the total becomes the positive charge of the proton. Put 1 up quark and 2 down quarks together, and the total becomes the neutral charge of the neutron. This is one of those details that sounds innocent until you stop and think about it. Fractional charge is not something everyday intuition prepares you for. No one opens a kitchen drawer and finds 2/3 of an electric spoon. Yet in the microscopic world, nature is perfectly content to assign quarks these fractional charges. The reason we do not meet isolated 1/3 charged objects in ordinary life is that quarks remain bound inside hadrons, where the total charges come out in the familiar whole combinations we observe directly. That feature alone would have made quarks interesting. But the story did not stop there. Physicists soon realized that up and down, quarks were not the only types. There are 6 kinds of quarks in total, usually called flavors, which is a wonderfully domestic word for something so subatomic. Along with up and down, there are strange charm, bottom and top. Some of these names sound as if the field was briefly run by a group of people who had been working too late, and decided that formal dignity had had its chance. But the name stuck, and in fairness they do make the subject easier to remember than if every particle had been named after an unfortunate committee report. The up and down quarks are the lightest and most stable in the sense relevant to ordinary matter. Strange quarks are heavier and show up in certain other hadrons. Charm, bottom, and top are heavier still and belong more to the realm of high-energy particle physics than to the furniture of daily life. The top quark in particular is astonishingly heavy compared with the others, and decays so quickly that it does not form ordinary hadrons in the usual way. But the existence of these 6 flavours tells us something important. Nature does not just have one kind of quark repeated over and over. It has a family of related elementary particles with different masses and roles. For the world around us, though, the essential pair remains up and down. A proton is mostly an up and down quark story. A neutron is mostly an up and down quark story. Nuclei, stars, chemistry, your own body, the crust of the earth, the oxygen in the air, and the calcium in your bones all depend at some level on hadrons built from these light quarks. In that sense, the visible world is a remarkably successful long-term collaboration between the up quark, the down quark, the electron, and the forces that let them behave themselves just enough to build stable matter. Still, the moment one says quarks are the unseen building blocks, a reasonable objection appears. If they are real, why are they unseen? Not just hard to see, but never found alone. Why do experiments reveal their effects inside hadrons, but not tidy little individual quarks sitting on detector screens waving politely to the camera? This is one of the defining features of the whole subject, and it has a name. Confinement. Quarks are confined by the strong interaction. The force between them does not let them separate freely under normal conditions. If you try to pull quarks apart, the energy stored in the force between them increases rather than fading away in the simple way common sense might expect. Eventually, if you pump enough energy into the system, you do not get a lone quark popping free in the ordinary sense. Instead, that energy can produce new quark-antiquark pairs, and what you end up with are more hadrons rather than isolated quarks. Nature, in effect, would rather make additional bound particles than hand you a single quark on its own. This is one of the reasons quarks remained controversial for a time. At first, some physicists wondered whether they were merely a mathematical device, a clever bookkeeping system for organising hadrons rather than genuine constituents. After all, science has seen useful abstractions before. You can classify things with tools that are not themselves physically real. If quarks could never be isolated, perhaps they were only a formal trick. But the accumulating evidence from scattering experiments, hadron spectra, and the emerging theory of the strong interaction made the case harder and harder to resist. Quarks were not just convenient labels. They behaved like real internal constituents with definite properties. The turning point came when high-energy experiments began probing the proton deeply enough to reveal point-like structure within it. Electrons fired at protons did not scatter as though they were hitting a smooth, indivisible blob. They scattered as though the proton contained smaller localized components. This did not produce a jar of quarks on a laboratory shelf, but it provided strong evidence that something quark-like was really there inside. The proton was not featureless. It contained internal objects that carried momentum and charge in just the kind of way the quark picture suggested. Even so, quarks remain hidden in a very particular sense. We infer them, model them, and see their signatures in experiments, but we do not isolate them as free particles in the world of ordinary matter. This makes them feel strange in a way that electrons do not. Electrons can be knocked loose, guided through circuits, trapped, accelerated and studied one by one. Quarks live under stricter house rules. They are elementary, but they are not solitary. That might make them seem less real to the imagination, but it should not. Plenty of real things are known through their effects rather than direct visual display. No one has ever looked at gravity sitting in a jar. We know it by what it does. In the same way, quarks earn their reality through the consistency and power of the theory that describes them, and through the wide range of experiments their existence helps explain. They are not visible in the ordinary sense, but they are deeply woven into the successful structure of modern particle physics. There is another layer to quarks that makes them even more interesting. In addition to familiar properties like charge and mass, quarks carry something called color charge. Despite the name, this has nothing to do with visual color. No proton is secretly 1/3 blue in a way that would improve the decor. Color charge is the kind of charge associated with a strong interaction, just as electric charge is associated with electromagnetism. Quarks come in 3 color varieties, and the strong force acts between these color charges through the exchange of gluons. This idea sounds fanciful until you see what it accomplishes. It explains how quarks can obey the rules of quantum mechanics, while still combining into hadrons in the observed ways. It explains the structure of baryons and mesons. It underlies the entire theory of the strong interaction, known as quantum chromodynamics. That theory is one of the great achievements of modern physics, though it is not especially famous at dinner parties unless you attend very specialized dinner parties indeed. Color charge also helps explain why quarks cannot be considered in isolation inside hadrons as if they were little independent pellets. The gluons that bind them together themselves carry color charge, which means the force carriers interact with one another as well. This makes the internal life of hadrons much richer and more complicated than the behavior of electrically charged particles in simpler systems. The strong interaction is not just a quiet tether between quarks, it is an active, self-interacting field that contributes substantially to the whole structure and mass of the hadron. So when we describe quarks as building blocks, it is worth remembering that they do not simply sit there providing raw material. They are participants in an intense dynamical system. They exchange gluons, they move, their momenta change. Additional quark-antiquark pairs can flicker into the picture as part of the quantum state. The proton is still often described as having 3 valence quarks, meaning the core quarks that determine its basic identity. But that is not the same as saying the interior contains only 3 quietly seated particles and nothing else. The full picture is far livelier. In that sense, quarks are both simpler and stranger than the old idea of solid constituents. Simpler because they help reduce the bewildering variety of hadrons to combinations of a smaller set of elementary objects. Stranger because those objects cannot be peeled out and inspected individually like screws from a machine. Their reality is inseparable from the theory that describes how they are confined, how they interact, and how they collectively generate the properties of hadrons. There is something almost philosophical about that. We began with the hope that matter would resolve into final little things. Instead, we found quarks, which are indeed more fundamental than protons and neutrons, but which do not present themselves as tiny isolated marbles. They are fundamental yet relational, real yet permanently bound, essential yet hidden. The universe has a way of granting simplicity only after first making us give up the wrong picture of what simplicity would look like. Even the names of the quark flavors hint at the history of that process. Strange quarks were named because the particles containing them behaved in ways that seemed unusual. Charm was introduced when theory suggested a missing partner in the pattern. Bottom and top arrived later as the family expanded. The list did not emerge because someone wanted an unnecessarily baroque particle menu. It emerged because experiments and theory kept pointing to a deeper order that required it. And once that order was recognized, the quark family turned out to be one of the central organizing principles of modern particle physics. Yet for all 6 flavors, ordinary matter is still dominated by the lightest pair. Up and down quarks are the practical workhorses of the hadronic world around us. The proton and neutron are stable enough to build nuclei, and nuclei are stable enough to build atoms, and atoms are stable enough to build chemistry, and chemistry is stable enough to produce the sort of creatures who lie awake at night wondering what a hadron really is instead of getting the sensible amount of sleep they were always advised to get. That long chain of consequence is worth appreciating. Quarks may be unseen, but their influence is everywhere. Without them, there are no protons in their current form, no neutrons in their current form, no atomic nuclei, no stars as we know them, no periodic table, and no ordinary matter arranged into the forms we inhabit and observe. The hidden building blocks are not marginal. They are buried at the foundation of the visible world. Still, understanding quarks alone is not enough. Knowing that protons contain quarks is like knowing that a bridge contains steel. It tells you something important, but not yet how the whole structure holds together under stress. The real secret of hadrons lies not only in the existence of quarks, but in the force that binds them so tightly that they never escape. And that means the next step takes us to the particles that carry that force, the gluons, and to the remarkable interaction that never seems willing to let go. Once quarks entered the picture, the proton became easier to describe in one sense, and much harder to understand in another. Easier, because we could say at last that the proton was not elementary, that it was built from smaller constituents, and that those constituents were quarks. Harder, because saying what the pieces are is not the same as saying how the whole thing manages to exist. If you tell me a bridge is made of steel, that does not yet explain how it stays suspended over a river. If you tell me a loaf of bread contains flour and water, that does not explain why it becomes bread instead of a mildly disappointing paste. In the same way, once physicists began taking quarks seriously, they still had to answer the deeper question. What is actually holding them together so tightly that a proton remains a proton and never casually falls apart into smaller bits on an idle afternoon? That is where gluons arrive, and with them the force that gives hadrons their deepest internal character. A gluon is the carrier of the strong interaction, the fundamental force that binds quarks together inside hadrons. At first glance, that can sound comfortingly familiar. We already know about force carriers in other parts of physics. Light is associated with photons. Electromagnetic interactions can be described in terms of exchange. Fine. So perhaps a gluon is just the strong force version of that, a sort of internal messenger passing notes between quarks and asking them to stay in formation. But that picture, while not entirely useless, is far too gentle. The strong interaction is not a polite suggestion that quarks remain near one another. It is an intense and peculiar force whose behaviour is unlike anything in ordinary experience. It is not merely strong in the sense of being large, it is strong in the sense of dominating the very existence of hadrons. To appreciate how unusual this is, it helps to step back and compare it with the force most people intuitively understand best: electromagnetism. Electric charge comes in positive and negative forms. Opposites attract, like charges repel. The farther apart two charged particles move, the weaker their electromagnetic pull becomes. This is already familiar from static electricity, magnets, circuits, and the general daily business of matter holding together without too much complaint. It is a force that reaches across long distances and fades with separation. The strong interaction does not behave that way in the crucial regime that matters for quarks. Quarks carry a kind of charge called colour charge, and it is this charge that gluons respond to. Despite the name, colour charge has nothing to do with visible colour. It is simply the label physicists gave to the type of charge associated with the strong force. And once that charge enters the story, the behaviour of the force becomes very strange indeed. Quarks can move around within hadrons, but trying to pull them farther apart does not free them in the way our instincts trained by everyday forces might expect. Instead, the interaction remains stubborn. The deeper you try to separate the quarks, the more energy you pour into the system. That is why the strong force is often described using the image of a stretched band, though even that picture is only a rough guide. With electric charges, increasing distance tends to weaken the force. With confined quarks, increasing distance tends to store more energy in the field between them, so rather than letting go, the strong interaction resists separation. Pull hard enough, and nature does not usually reward you with a lone liberated quark. It responds by converting the added energy into new quark-antiquark pairs, which then form new hadrons. In effect, the system would rather make more bound particles than allow a single quark to escape on its own. That feature is called confinement, and it is one of the most important facts in the whole subject. Gluons are not merely binding quarks the way a string binds two objects you could otherwise separate. They are part of a force structure that makes free quarks effectively absent from ordinary experience. Quarks live in hadrons because the strong interaction gives them very little choice about the matter. It is the force that never lets go, not because it is dramatic for the sake of drama, but because the mathematics and experiments both point to a world where quarks remain permanently bound under normal conditions. This has a huge consequence for how we think about hadrons. A proton is not a small bag with three quarks rattling around inside and a bit of glue to keep them from wandering off. The binding is much more profound than that. The gluons are not background helpers. They are essential players in the internal life of the hadron. In fact, one of the strangest and most important facts about hadrons is that gluons themselves carry the very colour charge associated with the strong interaction. That means gluons can interact with one another as well as with quarks. This sets the strong force apart from electromagnetism in a decisive way. Photons do not carry electric charge, so they do not directly interact with one another in the simple, ongoing way gluons do. Gluons, by contrast, are part of a self-interacting network. The force carriers are themselves caught up in the force. That makes the internal structure of hadrons much richer, and much harder to visualize with any simple mechanical model. It is not just quarks exchanging messages, it is a dense, active field of interaction in which the carriers themselves are participants in the process that holds the whole system together. This is one of the reasons why the proton turns out to be far more than three quarks in a quiet arrangement. Yes, the proton has three valence quarks, meaning the quarks that set its basic identity in quantum numbers. But the interior also contains gluons in abundance, and those gluons contribute substantially to the momentum, energy, and overall structure of the proton. The hadron is full of motion and exchange. It is not a static cluster. It is a dynamic bound state sustained by ceaseless interaction. There is a useful contrast here between what the eye of common sense wants and what quantum physics allows. Common sense wants a clear inside and outside, a handful of constituent parts, and perhaps a little glue in the corners. Quantum chromodynamics, which is the theory describing quarks and gluons, offers something far less tidy. It offers a world where the identity of the particle comes from a field-governed structure, where the constituents are confined, where the carriers interact with one another, and where much of the mass and momentum of the whole object arises from the energy of these interactions rather than from the simple bare masses of the constituents alone. That last point deserves real attention because it changes how we think about mass itself. It is tempting to imagine that a proton weighs what it weighs because it contains three quarks, and those quarks each bring along their own little share of mass. But that's not the main story. The up and down quarks inside the proton are relatively light. Most of the proton mass comes not from simply adding their individual masses together, but from the energy associated with the gluon field and the motion of quarks and gluons inside the hadron. In other words, the strong interaction does not just hold the proton together. It is responsible for most of the proton mass we observe. That is one of those facts that starts quietly and then becomes difficult to stop thinking about. Most of the visible mass of ordinary matter comes from protons and neutrons. Most of the mass of protons and neutrons comes from the energy of the strong interaction. So the solidity and heft of the world around you owe an enormous amount to gluons and the restless internal binding energy of hadrons. The mug in your hand, the floor under your feet, the bones in your body, the mountains outside, if you happen to be somewhere with mountains and not just an aggressively determined row of apartment buildings, all of that draws much of its mass from the energetic life of quarks and gluons bound together by the strong force. That makes gluons far more central to ordinary existence than their relative obscurity would suggest. The electron is famous because electricity is obvious and practical. The photon is famous because light is difficult to overlook. Gluons have a less glamorous public image, perhaps because they remain hidden inside hadrons and rarely turn up in beginner conversations unless someone has made the generous mistake of asking a physicist how matter really works. But hidden is not the same as unimportant. Gluons are among the main reasons the visible universe has the mass it does. There is another peculiarity of the strong interaction that gives gluons a special role. At extremely short distances, quarks behave as though they are less tightly bound. This feature is called asymptotic freedom. The phrase sounds like the title of a philosophy lecture or a particularly ambitious jazz album, but the idea is concrete. When quarks are extremely close together, the effective strength of the strong interaction becomes weaker. This means that inside a hadron, under very short distance conditions, quarks can behave almost as if they are moving more freely. Yet when one tries to separate them to larger distances, the force becomes effectively confining and refuses to let them drift apart. This is one of the strange balances at the heart of hadronic matter. Very close together, quarks are comparatively less constrained. Pull them apart and the force tightens its grip. So the strong interaction is not simply strong in a uniform way at every distance, its behaviour changes with scale. That scale-dependent behaviour is one of the triumphs of the theory, and one of the reasons quantum chromodynamics became such an important part of modern particle physics. It explained how quarks could appear nearly point-like in high-energy scattering experiments and yet never show up freely in isolation. The role of gluons in this theory is absolutely central. They are not optional corrections attached after the fact. They are the very means by which the colour-charged world of quarks is held together. Without gluons, there is no strong interaction as we know it. Without the strong interaction, there are no stable hadrons. Without stable hadrons, there are no protons and neutrons to build nuclei. Without nuclei, ordinary atoms never come together in the familiar way. The whole architecture of visible matter depends on this hidden force and the particles that carry it. There is also an important distinction to make between the strong interaction inside hadrons and the residual force that binds protons and neutrons together inside atomic nuclei. These are related but not identical in the everyday way one might first imagine. Inside a proton, quarks are bound directly by gluons through the fundamental strong interaction. Inside a nucleus, protons and neutrons are held together by what can be thought of as a leftover or residual effect of that deeper force. It is a bit like how neutral atoms can still attract each other under certain circumstances even though their net electric charge is balanced. The analogy is not perfect, but it helps. The force between nucleons in a nucleus is not the raw quark binding force exposed in simple form. It is a secondary consequence of the more fundamental strong interaction at the quark level. That distinction matters because it reminds us how deeply nested the world of matter really is. The proton looks like one particle at ordinary scales. Inside it, gluons bind quarks. Then protons and neutrons, themselves composite hadrons, participate in the residual strong force inside nuclei. Then nuclei and electrons form atoms. Then atoms form molecules. Then molecules build chemistry and materials and life. Each layer looks stable from above and complicated from below. Gluons belong to one of the deepest layers in that visible stack. All of this also helps explain why hadrons are so difficult to picture honestly. If the proton were only 3 quarks, one might still be tempted to sketch them as tiny balls joined by little springs. Not right, perhaps, but tolerably charming. Once gluons and their self-interaction enter the story, that picture becomes much too simple. The interior of a hadron is better understood as a constantly shifting quantum system, in which quarks carry colour charge, gluons mediate and participate in the interaction, and the entire bound state is defined by this activity. The proton is stable, yes, but it is not still. It is structurally alive with internal motion. One consequence of this is that the proton momentum is shared among more than just the valence quarks. Experiments show that gluons carry a substantial portion of the proton momentum. So even if you begin with the thought that a proton is made from 3 quarks, the actual distribution of what the proton is doing internally turns out to be far more involved. The gluons are not passive threads holding the object together while the quarks do all the meaningful work. They are active carriers of energy and momentum, helping define the measurable properties of the proton itself. That is part of what makes the subject so satisfying once one becomes used to its stubbornness. At first, the hiddenness of gluons can make them seem almost hypothetical in the casual imagination, like some extra machinery physicists invented, because the first explanation was not quite busy enough. But the deeper one looks, the more unavoidable they become. They explain confinement, they explain the binding structure of hadrons, they explain why most proton mass is not just quark mass. They explain why the interior of the proton is not a tidy arrangement of three static objects. They are woven through the very identity of hadronic matter. It is also worth noticing the irony in the name. Glue suggests something sticky, perhaps quiet, perhaps practical, perhaps applied by someone wearing old clothes in a well-ventilated workshop. But gluons are not a gentle adhesive. They are the carriers of an interaction so strong that it keeps quarks permanently confined, builds most of the mass of visible matter, and turns the interior of the proton into one of the most dynamically rich systems in all of ordinary physics. If anything in science has ever suffered from an undersell, it may be the gluon. And yet the name has its charm because in the broadest sense, gluons do hold things together. They are what make hadrons possible. They are the reason quarks do not drift into freedom and leave matter structurally unemployed. They make the proton more than a list of constituents. They make it a bound state with integrity, heft, and persistence. The force never lets go because the universe seems deeply committed to keeping quarks in hadronic company. Once you begin to see that, the proton stops feeling like a simple particle and starts feeling like a tightly governed internal world. Quarks contribute identity. Gluons contribute binding, energy, momentum, and much of the mass. The whole thing is held together by a force that behaves in its own distinctive way, quite unlike the gentle long reach of electromagnetism. And because that force is so powerful and so confining, the proton is never just a shell with contents. It is the ongoing outcome of the interaction itself. That brings us naturally to the next layer of the story, because once gluons are doing all this work inside the proton, it becomes impossible to keep pretending the proton is just three neat constituents and a bit of strong force wallpaper. The interior is busier than that. There is a constant, restless sea of additional activity inside every proton, and that hidden crowd is part of what makes hadrons so much stranger than their schoolbook portraits ever suggested. And this is where the proton starts becoming even less polite to our expectations. It would already be surprising enough if the proton were simply three quarks held together by gluons in a stable arrangement. That alone would be enough to retire the old picture of matter as tiny solid pellets. But once experiments improved and theory matured, physicists had to accept something more unsettling and much more interesting. The proton is not only a home for its three valence quarks, it also contains a restless sea of additional activity, a shifting internal crowd that appears and disappears as part of the quantum life of the whole object. The phrase sea quarks is often used here, and while it sounds poetic, it is really an attempt to describe something technically specific. The proton has three valence quarks that define its core identity. Those are the two up quarks and one down quark that give the proton its overall charge and basic classification. But inside the proton there is also a continual presence of gluons and short-lived quark-antiquark pairs that flicker into existence and then disappear again. These transient pairs are not the same thing as the valence quarks. They do not determine the proton identity in the same direct way, but they are real parts of the proton quantum state, and they contribute to its behavior. That distinction between valence quarks and sea quarks is essential, because it helps us avoid one of the most common misunderstandings. When people first hear that a proton is made of three quarks, they understandably imagine that those three quarks are the whole story. 3 ingredients, job done. But the proton is not a quiet container. It is a quantum system full of exchange, motion, and fluctuations. The valence quarks are the backbone of the description, but the full interior includes much more than just those three. To see why this happens, it helps to remember what gluons are doing. Gluons carry the strong interaction, and unlike photons in simple electromagnetic situations, gluons interact with one another. That means the gluon field inside the proton is not a passive background, it is active and self-interacting. Under the rules of quantum physics, that activity makes it possible for quark-antiquark pairs to appear briefly as part of the internal state. Energy and interaction at very small scales do not sit still. The proton is not a mechanical assembly. It is a bound quantum object whose internal structure includes constant fluctuations. This is one of those moments where language starts to struggle a little. The words appear and disappear are useful, but they can sound too much like miniature objects popping in and out of existence like badly behaved theatre props. What physicists really mean is that the proton state includes these transient contributions. The hadron is described not by one frozen arrangement, but by a quantum mixture of possibilities, interactions, and contributions that together produce the stable object we call a proton. The C-quarks are part of that fuller description. There is something almost counterintuitive about this. We're used to identity being tied to stable ingredients. If I tell you a loaf of bread contains flour, water, yeast, and salt, you do not generally expect a changing cloud of temporary baguettes to flicker in and out of the dough while no one is looking. But the proton is not made according to bakery rules, sadly for all of us. It is built according to quantum chromodynamics, and that theory permits, and indeed requires, a much livelier interior than any kitchen would tolerate. One useful way to think about it is to imagine that the proton is less like a sealed box of 3 marbles and more like a tightly bound storm system. The storm has a stable identity. It remains one organised phenomenon. But inside it there is constant movement, exchange, turbulence, and shifting structure. Now even that image has limits, because storms are classical and protons are quantum objects, but it captures something important. Stability on the outside does not mean stillness on the inside. This internal sea matters because it contributes to measurable properties of the proton. It is not decorative complexity added by theorists who feared simplicity might catch on. The momentum of the proton is shared among valence quarks, C-quarks, and gluons. The spin of the proton, which at one time many people hoped would be straightforwardly explained by the spins of the 3 valence quarks, turned out to be far more subtle. The C and the gluon contributions matter there as well. Even the apparent mass and internal energy distribution of the proton reflect this restless internal structure. In short, the C is not a minor correction. It is part of the real proton. This becomes especially clear in high-energy scattering experiments. When fast-moving particles are fired into protons, the results reveal not a smooth object and not a simple trio of stationary constituents, but a complicated internal distribution of partons, a general word physicists often use in this context for the momentum carrying components inside a hadron. Depending on the scale and energy of the probe, what matters experimentally may be valence quarks, C-quarks, gluons, or some combination of them. The proton does not present the same interface under all conditions because its structure is scale-dependent. That idea can feel slippery at first, but it is central to the modern understanding of hadrons. The proton you meet in an everyday chemistry context is a stable, positively charged particle in the nucleus. The proton you meet in a high-energy scattering experiment is a dense internal system of quarks, antiquarks, and gluons sharing momentum in a way that depends on how closely you're probing it. These are not different protons. They are different levels of description of the same object. Nature is not being inconsistent. It is just refusing to fit inside one simplistic picture. Now, one might reasonably ask how this sea is possible if energy must be conserved. The answer lies in the quantum rules that govern fluctuations and interactions at very small scales. The proton is not borrowing reality in some lawless way. It is a fully allowed quantum state, and part of that state includes these transient contributions. The language of virtual particles often appears in these discussions, though that term can create its own confusions if treated too literally. The key point is not that little particles are violating the rules and sneaking about in secret. The key point is that the quantum description of the proton includes more than just 3 fixed quarks, because the strong interaction allows a much richer internal structure. This richness is especially important for gluons. Gluons can split into quark-antiquark pairs, and they can interact with one another in ways that keep the interior highly active. So the proton contains not just its valence quarks and a few extra guests drifting through the hallway. It contains a whole network of strong interaction dynamics that continually reshapes its internal content while preserving its overall identity. The proton remains a proton, but it does so through motion, not through stillness. That is one of the deepest lessons in the whole subject. We often associate stability with the absence of change. A stable chair sits there. A stable rock does not visibly reorganize itself every few moments. A stable institution, if such a thing exists, does not usually send half its staff in and out of existence before lunch. But in the quantum world, stability can emerge from intense ongoing activity. The proton is stable not because nothing happens inside it, but because the rules of the strong interaction organize that internal activity into a durable bound state. There is a nice irony here. The proton is one of the most stable particles in ordinary matter. It survives happily in atomic nuclei for timescales that are, for practical purposes, extraordinary. And yet inside that stable object is a constantly shifting sea. Calm on the outside, very busy within. One could make an unwise comparison to certain administrative departments, but perhaps this is not the moment. The sea also raises an important question about flavour. If the proton valence structure is 2 up quarks and 1 down quark, what kinds of quarks appear in the sea? The answer is that the sea can include up and down quark-antiquark pairs, and under the right conditions also strange quark contributions. Heavier quarks are less prominent in the ordinary proton sea because producing them requires more energy, but the internal structure is not limited in principle to just the simplest pairs. This means the proton, though built fundamentally as an up-up-down baryon, can contain a richer flavour content in its fluctuating interior than its basic label suggests. That was one of the reasons experimentalists became so interested in carefully mapping proton structure. The sea is not just there, it has a shape. Different components carry different fractions of the proton momentum. Some quark types may appear more often than others. There can be asymmetries in the sea that are not obvious from naive symmetry arguments. The proton is not an evenly stirred soup. It has detailed internal structure, and measuring that structure is one of the great experimental projects of modern particle physics. This is where the old image of a proton as a tiny billiard ball becomes completely hopeless. A billiard ball has a centre, a surface, and a fairly boring internal biography. The proton has no simple little hard shell, no tidy separation between inert contents and containing wall, and no reason whatsoever to respect the idea that one stable particle must correspond to one frozen arrangement of parts. Instead, it is a hadron, a bound state governed by quantum chromodynamics, with valence quarks, a gluon field, and a sea of quark-antiquark activity, all contributing to what it is. Even the size of the proton becomes more interesting in this light. It is not the size of a tiny hard bead. It is the characteristic scale over which this bound state extends, the region in which its internal quark and gluon structure is distributed. Asking where a quark is inside the proton does not have quite the same meaning as asking where a raisin is inside a pudding. The proton interior is described probabilistically, dynamically, and in terms of momentum distributions and field interactions. That does not make it vague in the sense of being poorly understood. It makes it quantum. One of the most fascinating consequences of this restless sea is how it changes with the energy scale at which the proton is examined. At lower energies, the proton may be effectively described in one way. At higher energies, where probes resolve finer details, the C and gluon content become more and more important. In fact, at very high energies, the gluon population becomes extremely significant. The proton begins to look less like a 3-quark object, with a few additional complications, and more like a densely populated system in which gluons play a dominant role. The simple schoolbook version starts to feel like a polite summary written for people who need a good night's sleep. And yet that schoolbook version is not useless. It captures the core identity. The proton really is a baryon with 2 up quarks and 1 down quark as its valence structure. That matters. It explains its charge. It helps classify it. It is the starting point. The problem comes only when the starting point is mistaken for the whole story. In hadron physics, the whole story is always more active than the first sentence suggests. This matters beyond pure curiosity, because proton structure influences the outcomes of high-energy collisions. When protons are smashed together in accelerators, it is not the proton as a single rigid object that collides in the simplest sense. Rather, the interactions occur between their constituent partons, quarks, and gluons carrying various fractions of the proton momentum. To predict and interpret collision results, physicists need detailed knowledge of how that momentum is distributed among valence quarks, C-quarks, and gluons. The restless sea is not just a philosophical flourish, it is part of the practical machinery of particle physics. There is something wonderful about that. An object as apparently ordinary as the proton turns out to contain enough hidden complexity to keep entire research programs occupied for decades. We're not talking here about some speculative ghost particle glimpsed once at the edge of a detector. We're talking about one of the main ingredients of visible matter, and it is still rich enough inside to surprise us, still subtle enough to demand new experiments, still structured enough that mapping it remains an active scientific task. The common things, once again, prove to be some of the strangest. The sea also helps us see why hadrons are such unusual composite objects. In ordinary life, a composite thing is usually identifiable by its assembled parts. A watch has gears, a bicycle has wheels and a chain. A sandwich, if competently prepared, has visible layers. A hadron does not work that way. Its constituents are not laid out as a transparent arrangement of component pieces. They are bound, fluctuating, and described through quantum fields and probability distributions. The proton is composite, but not in a visually mechanical sense. It is composite in a field-theoretic and dynamical sense. And because of that, the very meaning of what is inside becomes more subtle. The sea is inside the proton, yes, but it is not inside the way pebbles are inside a jar. It is part of the proton state. It reflects the allowed fluctuations of the strong interaction. It helps determine how the proton behaves under different probes. It contributes to the distribution of momentum and spin. It is not an optional embellishment, it is part of what the proton is. If all this sounds a little unruly, that is because it is. The proton is an unruly success. It is one stable particle built out of an internal world that never entirely settles down. The strong force does not merely lock 3 quarks in place and call it a day. It produces a living quantum system whose apparent simplicity from afar hides a dense and shifting interior. And once you accept that, a great many mysteries begin to look less mysterious. Of course, the proton mass is not just a trivial sum. Of course, the spin is not explained by a childishly simple accounting of 3 quark arrows. Of course, high-energy scattering sees more than 3 neat objects. The proton has been telling us all along that it is busier than it looks. There is another quiet lesson in this as well. The sea does not destroy the proton identity. The proton remains one object. It has a definite charge, a definite baryon number, a definite set of observable properties. Complexity inside does not mean ambiguity outside. The hadron is proof that nature can build stable individuality out of internal fluctuation, that a system can be dynamically crowded and still globally well defined. Again, one is tempted to compare this to human beings, but perhaps that would be unfair to the proton, which at least obeys very precise equations. By now, the older notion of matter as nested hard spheres has more or less dissolved completely. Instead, we have a proton with valence quarks defining its identity, gluons carrying the strong interaction and much of the momentum, and a sea of quark-antiquark pairs participating in the full quantum state. This is what the inside of ordinary matter looks like once you stop asking it to be simple in the old classical way. And the next thing we have to face is how these ingredients come together to produce one stable particle at all, because it is one thing to say that the proton contains 3 valence quarks, gluons, and a restless sea, and another thing entirely to explain how all that activity manages to produce something with one mass, one charge, one spin, and one stubbornly persistent identity. That is the real puzzle, because once you accept that the proton is not just 3 quarks sitting quietly together, the obvious question becomes how all that motion and interaction manages to produce one single particle with definite properties. How does a system that is internally so busy still present such a clear and reliable identity to the rest of the universe? How does a proton remain one proton every time, rather than becoming a vague statistical shrug with no fixed character? That question takes us right to the heart of what a hadron really is. The simple version says that a proton is made from 3 valence quarks, specifically 2 up quarks and 1 down quark. That is true, and it remains a useful starting point. Those 3 quarks fix the proton basic identity. They determine its overall electric charge. They determine that it belongs to the baryon family. They distinguish it from the neutron, which swaps one of those up quarks for a down quark. In that sense, the valence quarks are the skeleton of the proton description. They tell you what kind of hadron you are dealing with. But the proton is not just a label attached to a quark inventory. It is a bound state. That means its properties do not come from a simple list of contents alone. They come from the total quantum system formed by those contents, and the strong interaction binding them together. The 3 valence quarks are essential, but once they are inside the proton, they are not independent little objects that keep all their individuality in the straightforward way common sense would prefer. They are part of a deeper whole, and the whole has properties that cannot be understood by treating the quarks like tiny separate marbles in a bag. This is one of the great recurring lessons in physics. A stable system often behaves as more than the sum of its parts, but in hadron physics that statement becomes very literal. The proton charge is easy enough to begin with. 2 up quarks each carry a positive 2/3 of the proton charge, and 1 down quark carries a negative 1/3, so together they give the proton its overall positive charge. That part sounds pleasantly neat, almost suspiciously so. It feels like one of the last places where the universe allows us to do clean arithmetic and move on. But when it comes to other properties, especially mass and spin, the neatness evaporates very quickly. Take mass. If you were trying to understand the proton using only everyday intuition, you might assume that its mass is mostly just the sum of the masses of its 3 valence quarks. 3 pieces, add them up, and there is your proton. But that is not what nature does. The up and down quarks are relatively light. If you add their bare masses together, you get only a small fraction of the proton total mass. Most of the proton mass comes from the energy of the strong interaction itself, from the motion of quarks and gluons inside the proton, and from the binding dynamics of the whole system. That is a very strange fact when you first let it settle in. Most of the mass of the proton does not come from the simple rest masses of the quarks we name as its main ingredients. It comes from the energy locked into the proton internal life. In other words, the proton weighs what it weighs largely because the strong force is doing such intense work inside it. The hadron is not heavy because it contains 3 tiny heavy objects. It is heavy because binding energy and motion inside the bound state contribute overwhelmingly to the total mass. This tells us something essential about what it means for 3 quarks to become a proton. They do not merely occupy the proton. They participate in a dynamic structure that generates the proton properties. The proton mass is an emergent feature of the whole system. It belongs to the hadron as a bound object, not merely to the isolated pieces considered one by one. That is why the proton feels much more substantial than a naive quark inventory might lead you to expect. The same kind of surprise appears with spin, and in some ways it is even more revealing. Spin is a quantum property that, in simplified descriptions, is often compared to angular momentum, though not in the ordinary mechanical sense of something literally spinning like a tennis ball. The proton has a definite spin. That is part of its identity. For a long time it seemed tempting to think that the proton's spin should be straightforwardly explained by the spins of its three valence quarks. Three quarks, each with their own spin, combine them appropriately, and one should be able to recover the proton total. But when physicists looked more carefully, that neat picture failed. The valence quark spins account for only part of the proton total spin. The rest involves contributions from gluons and from the orbital motion of quarks and gluons inside the proton. In other words, the proton spin is not just a static property attached to the three core quarks. It is a collective feature of the full internal system. The proton carries one stable value of spin outwardly, but inwardly that value is assembled from several sources whose interplay is anything but simple. This matters because it shows us how a hadron achieves unity. The proton is not one thing because its interior is simple. It is one thing because the strong interaction organizes complexity into a stable quantum state with well-defined external properties. The unity is real, but it is the unity of a system, not the simplicity of a single indivisible bead. There is a useful analogy here, though like all analogies it breaks if leaned on too heavily. Think about a musical chord. A chord is one audible event, one recognizable sound, but it is made from multiple notes interacting in a structured way. Remove one note and the chord changes identity. Add tension between notes and the overall character shifts. The whole sound is real and unified, but it cannot be reduced to a single tone without losing what it is. A proton is of course not a chord, and quarks are not carrying tiny violins, though one suspects the gluons would insist on percussion. Still, the principle is helpful. A stable whole can emerge from multiple components, whose relationship matters as much as the components themselves. That is why the old mental picture of three quarks sitting in the proton like three peas in a pod is too crude. The quarks are moving. They exchange gluons. Their momentum changes. The gluons themselves carry momentum and interact with one another. This sea of quark-antiquark pairs contributes as part of the proton full quantum structure. And all of this takes place under the rules of quantum chromodynamics, where confinement ensures that the quarks remain bound and the proton appears as a single particle to the outside world. What gives the proton its persistence is not stillness, but organization. The system is active, yet it does not dissolve into chaos because the strong interaction is not random. It is rule-governed, extremely powerful, and capable of producing bound states with sharply defined properties. So the proton stays itself because the allowed internal activity is all happening inside a framework that preserves its overall identity. 2 up quarks and 1 down quark remain the valence core. The total charge remains positive. The total baryon number remains fixed. The total spin remains the proton spin. The internal details fluctuate, but the larger structure holds. This is one of the most important conceptual moves in the whole subject. We stop asking how 3 tiny solid objects combine mechanically, and start asking how a quantum field theoretic system, built from quarks and gluons, produces a single stable hadron. That shift may sound technical, but it changes everything. Instead of treating the proton as a small machine, we treat it as a bound state in a quantum theory. The language becomes less friendly to ordinary imagination, but much closer to the truth. And that truth has another interesting consequence. The proton properties are not simply inherited from its constituents. They are reshaped by the interaction. The 3 valence quarks set the foundation, yes, but once the strong interaction binds them into a hadron, the result is not just those quarks with the serial number still visible. The result is a new object whose measurable behaviour belongs to the whole system. This is why hadrons are such good examples of emergence in physics. Something new appears at the level of the bound state. Not magical, not mysterious in the vague sense, but genuinely new in the sense that the whole has features requiring the collective description. This is also why high-energy experiments are so important. When physicists probe the proton, they are not simply counting the 3 valence quarks and going home satisfied. They are mapping how momentum is distributed, how scattering reveals partonic structure, how gluons contribute, how spin is assembled, how the sea behaves, and how all of that changes with energy scale. The proton is one object outwardly, but inwardly it is a rich system whose collective properties can only be understood by seeing how those ingredients behave together. There is a very practical way to think about this. Suppose you ask what makes water wet. You cannot answer by pointing only to an isolated hydrogen atom or an isolated oxygen atom and saying the wetness is probably in there somewhere. Wetness is a property that arises when many molecules behave collectively under certain conditions. In a much deeper and more technical way, the proton has a similar lesson. Its mass, spin, and internal structure are not all sitting neatly inside one isolated quark, waiting to be discovered. They arise from the collective bound state formed by quarks and gluons under the strong interaction. Now it is important not to push that comparison too far. Wetness is a macroscopic emergent property, while the proton is a single quantum object, but the broader idea holds. Some properties belong to the system level, not to the pieces in isolation. The proton is not hiding its true nature from us. It is simply a case where the true nature is collective. This helps explain why baryons like the proton and neutron are so robust and so central to matter. They are not fragile piles of parts. They are strongly bound states. The energy scale of the strong interaction is immense compared with most everyday physics. That is why it takes high-energy processes to significantly disturb hadronic structure. It is also why protons, once formed, are so durable. The same force that makes their interior complicated also makes their identity stable. There is another way in which 3 quarks become something much more, and it has to do with confinement itself. Quarks cannot simply be thought of as 3 independent constituents that happen to travel together. They only make physical sense in the hadron through their confined relationship. A free quark is not part of ordinary observed reality. The hadron is the natural physical form in which those quark degrees of freedom appear. So the proton is not just a convenient group of 3 smaller objects, it is the actual realized state permitted by the rules of the strong interaction. That makes the hadron feel less like an assembled object and more like a solution. A proton is what you get when 2 up quarks and 1 down quark are bound under the strong interaction, in a colour-neutral state that nature allows to exist stably. It is not a loose arrangement chosen at whim. It is a permitted configuration in a very strict theory. And because the theory is so strict, the resulting object comes with definite measurable properties again and again. Colour neutrality is part of that story as well. Quarks carry colour charge, and hadrons must combine these charges in such a way that the total state is colour neutral. That requirement is not decorative. It is one of the central rules determining what kinds of bound states are physically realized. In a baryon, the 3 quarks combine their colour charges in a specific way to form an overall neutral state with respect to the strong interaction. That colour-neutral whole is what appears as the hadron we observe. Another reminder then that the hadron is defined not just by the presence of quarks, but by how they combine under the rules. There is something satisfying about that level of constraint. The universe is not improvising badly here. The proton is not a lucky accident held together by optimism. It is a lawful quantum structure, one that arises because the strong interaction allows and indeed favours certain confined combinations. 3 quarks become a baryon not by vague togetherness, but by very particular rules involving colour, confinement, energy, and symmetry. And symmetry matters a great deal in all of this. The proton is not just any three-quark arrangement. It belongs to a class of states with specific quantum numbers. Those numbers encode conserved properties and allowable structures. They are the bookkeeping of the deep theory, but bookkeeping in physics is often the closest thing we have to a confession from nature. The proton keeps the same charge, the same baryon number, the same spin, and the same overall identity because the underlying rules preserve them. This is why hadron physics can feel so paradoxical at first. The proton is one of the most familiar particles in the world, yet the reason it is familiar is not because it is simple. It is familiar because the strong interaction builds an extremely reliable complexity. Three quarks become something much more because the strong force turns them into a collective object, with new emergent properties and remarkable stability. The proton is not the sum of three quarks sitting still. It is the outcome of their confinement, motion, gluon exchange, C activity, and shared participation in one color neutral bound state. By now, then, we can say more honestly what a proton is. It is a baryonic hadron with three valence quarks, yes, but it is also a strongly bound quantum system whose mass comes largely from interaction energy, whose spin is shared among several internal sources, whose interior contains gluons and C quarks, and whose unity depends on the rules of quantum chromodynamics. That is what three quarks become when the force between them is strong enough and the theory underlying them is rich enough. They become not a cluster, but a new physical thing. And once that much is clear, another question naturally pushes forward. If quarks are so central, if they define hadrons and help build the visible world, then why are they never found alone? Why does nature allow us protons, neutrons, mesons, and all manner of hadrons, yet refuses to hand over a single free quark for inspection? That puzzle leads directly into the strange logic of confinement itself, and into the question of why quarks are never seen outside the particles they help create. That question about why quarks are never found alone opens onto an even larger puzzle, because the proton is strange in more ways than one. It is not just that its constituents refuse to step outside by themselves. It is also that the proton ends up carrying properties that are far richer than the simple schoolbook picture would lead you to expect. If someone tells you a proton is made from two up quarks and one down quark, that sounds like the beginning of a straightforward accounting exercise. You imagine three small ingredients going into one familiar particle, and you assume the rest is just a matter of adding up what each one contributes. But the proton does not cooperate with that kind of arithmetic for very long. Its mass is far larger than a naive quark tally would suggest. Its spin is shared out in ways that took physicists decades to begin untangling, and the more carefully we measure its internal structure, the more it becomes clear that the proton, for all its apparent simplicity, is one of the most layered objects in ordinary matter. This is part of what makes the proton such a satisfying subject. It is not obscure. It is not some rare particle that appears only for a blink in a detector and then disappears before anyone can ask it a decent question. The proton is everywhere. It is sitting in every atomic nucleus with a positive charge. It is part of the material structure of planets, people, plants, and stars. It is one of the basic residents of visible matter. And yet once you look inside it, the story becomes unexpectedly difficult. The object that seems so dependable at the surface turns out to be carrying deep questions about where mass comes from, how internal motion becomes a stable quantum property, and why the rules of the strong interaction produce the visible world in the form that they do. Mass is the first of those surprises because it looks at first like the easiest thing to explain. Mass feels straightforward in everyday life. Something is heavy or it is not. Lift a bag of groceries and your arms report back with admirable honesty. Push a piece of furniture across the floor, and the universe makes its opinions known very quickly. In ordinary experience, mass seems like the most obvious kind of property, the kind you can trust even when everything else becomes theoretical and slightly moody. So it would be reasonable to expect the proton mass to come from the masses of the particles inside it. After all, if the proton is made of quarks, then surely its mass is just the sum of quark masses, perhaps with a little extra accounting around the edges. But that is not how the proton works. The up and down quarks inside the proton are relatively light. If you simply add together the bare masses of 2 up quarks and 1 down quark, you get only a small fraction of the proton total mass. Most of the proton mass comes from something else. It comes from the energy of the strong interaction itself, from the ceaseless motion of quarks and gluons inside the proton, and from the binding dynamics that hold the whole hadron together. In other words, the proton is not massive mainly because it contains 3 heavy ingredients. It is massive because the strong force creates an intense, energetic internal system, and that energy contributes overwhelmingly to what we measure as mass. That is one of the most important facts in all of particle physics, and it still feels surprising no matter how many times you hear it. Much of the mass of ordinary visible matter comes not from tiny bits of substance carrying their own private little weights, but from energy locked into the dynamics of hadrons. The proton is heavy because it is busy. The neutron is heavy for much the same reason. And since protons and neutrons account for most of the mass of atoms, the heft of the everyday world is largely a consequence of the strong interaction, doing its relentless internal work inside hadrons. There is something deeply instructive in that. It tells us that matter is not built the way common sense first imagines. We want solidity to come from solid ingredients. We want weight to come from little weighted parts. We want a proton to feel substantial because it contains 3 sturdy quarks carrying most of the burden. Instead, the world gives us a bound quantum system whose mass is mostly the result of interaction energy. The familiar heaviness of stone, wood, metal, bone, and rain-soaked soil turns out to owe far more to invisible fields and confinement than to the bare masses of quarks alone. This does not mean the quarks are unimportant. Far from it. The quarks define the proton identity. They provide its overall electric charge and its baryon character. Without them, there is no proton in the first place. But once the proton exists as a hadron, the strong force does more than hold those quarks in place. It transforms the whole object into something with emergent properties that belong to the bound state rather than to the ingredients considered in isolation. The proton mass is one of the clearest examples of that transformation, and if mass is surprising, spin is perhaps even more troublesome. Spin is one of those concepts that physicists use constantly, and everyone else has to make peace with gradually. It is a quantum property, often compared with angular momentum, but it is not the same thing as a tiny ball physically spinning in space. That old image can be useful for the first few minutes and dangerous for the next several years. The proton has a definite spin. That is part of what it is. It affects how the proton behaves in magnetic fields and how it participates in interactions. In the broadest sense, spin is part of the proton identity as surely as charge and mass are. The tempting assumption is that if the proton is made of 3 valence quarks, then the proton spin should just come from the spins of those quarks. 3 ingredients, each carrying their own spin combined appropriately. Problem solved. There was a time when many people hoped the story might be close to that simple. But as experiments improved, especially those involving polarized scattering, it became clear that the valence quark spins do not account for the full proton spin on their own. That was a genuine shock. It meant the familiar picture was incomplete in a deeper way than expected. What followed was one of the great detective stories in modern particle physics. If the proton spin is not simply the sum of the valence quark spins, where is the rest coming from? The answer, as it turns out, is shared among several sources. Some of the proton spin does come from quark spin. Some comes from gluons. Some comes from the orbital motion of quarks and gluons inside the proton. In other words, proton spin is a collective property of the full dynamical system. It is not hidden inside one component waiting to be added up like change on a table. It is assembled from motion, field contributions, and the behavior of the bound state as a whole. That is difficult at first because spin sounds like it ought to be a personal property. This particle has this spin, that particle has that spin. End of story. But the proton reminds us that composite particles do not always inherit their properties in the most obvious way. The proton has one definite spin outwardly, yet inwardly that spin is distributed across several contributors whose interactions are anything but simple. The result is fixed. The route to the result is not. This is where the proton becomes a wonderful example of how physics moves beyond the intuitive picture of little objects carrying little traits. A hadron is not a bag of labelled pieces. It is a strongly bound quantum system, and the properties we observe can depend on the full internal arrangement of momentum, interaction, and angular motion. The proton spin problem was not just a technical annoyance. It was a sign that the proton internal life is much richer than the early quark model alone would suggest. The phrase proton spin crisis was used for a time because the discrepancy between expectation and measurement was so striking. It sounds dramatic, perhaps slightly theatrical, but it captured the mood. The proton had once again refused to be simple. It had once again shown that what looked like a straightforward matter of accounting was actually a question about collective structure inside one of the most familiar particles in existence. And although a great deal of progress has been made, the full detailed decomposition of proton spin remains a subtle and active area of study. That word active matters. The proton is not a solved relic. It is still a live research object. That in itself is extraordinary. One of the central building blocks of ordinary matter remains a subject of ongoing investigation at the deepest level. We're not still asking whether the proton exists or whether it carries positive charge. Those matters are mercifully settled. But we're still asking how exactly its inner momentum is partitioned, how gluons contribute to spin, how quarks enter the story, how its mass emerges quantitatively from the strong interaction, and what the most faithful picture of its internal structure should be. Part of the mystery comes from the fact that the strong interaction is difficult to calculate in the regime that matters most for hadrons. At extremely high energies and very short distances, the theory behaves in ways that allow certain calculations to be handled more cleanly. But at the scales relevant to the bound state structure of protons, the interaction becomes intensely non-trivial. Confinement, self-interacting gluons, quark fluctuations, and collective dynamics all enter the problem. The mathematics remains exact in principle, but extracting the observed properties of hadrons from that mathematics is demanding in the extreme. This is one reason why proton physics combines theory, computation, and experiment so tightly. One cannot simply write down a charming picture and trust that reality will follow along. The proton must be interrogated by scattering experiments, modelled using the tools of quantum chromodynamics, simulated on powerful computers, and interpreted with enormous care. The mystery is not there because science has failed. The mystery is there because the proton is genuinely complicated, and understanding it at a deep level takes work. The proton also teaches a useful lesson about the word mystery itself. In everyday language, mystery often means something vague, cloudy, perhaps romantic, perhaps impossible to pin down. In physics, a mystery is usually something much more concrete. It means there is a real measurable fact whose detailed explanation remains incomplete, or whose full internal mechanism is still being explored. The proton mass is not mysterious in the sense that we know nothing about it. We know a great deal. We know it arises largely from strong interaction dynamics. But to derive that result with full precision and intuitive clarity from first principles is one of the hard achievements of the theory. Likewise with spin. We know the broad sources, but the detailed internal bookkeeping remains subtle, and the proton continues to challenge our understanding. There is another kind of mystery in the proton as well, one that comes from its size and shape. It is tempting to imagine the proton as roughly spherical and tidy, perhaps because the mind likes to assign little roundness to particles whenever possible. But the proton is not a tiny hard ball with a clean surface. Its charge distribution, magnetic structure, and internal momentum profiles are all matters of careful measurement and theory. Depending on how one probes it, the proton reveals different aspects of its internal organization. This does not mean it changes identity from one moment to the next. It means that the proton, like all quantum systems, is described through distributions and probabilities rather than through miniature classical surfaces. Even something as apparently innocent as the proton radius became a subject of sustained attention and debate when different measurement methods appeared to give conflicting values. That sort of puzzle may sound like a detail fit only for specialists with heroic patience, but it matters because it shows again how the proton resists our instinct to treat it as completely straightforward. An object this common ought, one feels, to have the decency to reveal its size without incident. Instead, it became another reminder that hadronic structure must be measured and interpreted with great care. And this brings us back to the larger theme. The proton is mysterious not because it is exotic, but because it is foundational. If this were some obscure, short-lived particle produced only in violent collisions, its complexity would be easy to file away under the heading of advanced complications. But the proton is one of the main load-bearing pieces of visible matter. Its mass helps determine the mass of atoms. Its stability helps make matter durable. Its charge helps structure nuclei and chemistry, indirectly through the architecture of atoms. Its existence shapes stars, planets, and bodies. So when the proton turns out to be rich and difficult, the lesson is not limited to particle physics. The lesson is that the ordinary world rests on hidden structure more sophisticated than daily experience suggests. This is one of the most satisfying things about the subject if you're in the mood to be satisfied by complexity, which I realise is not everyone's idea of a restful evening, though I do think the proton tries its best. The world is not magical in the lazy sense. It is lawful all the way through. But the laws produce outcomes that are richer than the first simple story we tell ourselves. 3 quarks become a proton. Fair enough. But the proton mass comes largely from binding energy and motion. The proton spin is shared among quarks, gluons, and orbital contributions. The proton interior contains a sea of fluctuating activity. The proton size and structure depend on how it is probed. The proton remains one particle, but it does so through a collective internal world. There's also a philosophical edge to this, though it is best handled carefully. The proton suggests that identity in nature is often a matter of organized relationship rather than simple indivisible stuff. A proton is real. It is stable. It has definite properties. Yet those properties emerge from a bound state of constituents whose interactions are essential to what the proton is. The proton is not less real because it is composite. In some ways, it is more instructive precisely because it shows how stable individuality can arise from hidden dynamical structure. That idea has appeared before in physics. Atoms are not elementary, yet they are real and stable. Molecules are not elementary, yet they are real and stable. Stars are not elementary, yet they are very real, often inconveniently bright and structurally rich. The proton belongs to this lineage of systems whose unity is not threatened by internal complexity. The only difference is that the proton occupies a much deeper layer in the architecture of matter, where the relevant force is the strong interaction, and the internal rules are quantum mechanical in the full demanding sense. So why do protons have mass, spin, and so much mystery? They have mass because the strong interaction and the motion of quarks and gluons create an energetic bound state whose mass is far greater than the sum of bare quark masses alone. They have spin because the proton is a collective quantum system in which quark spin, gluon spin, and orbital motion all contribute to the final observed value. And they have so much mystery because the strong force is powerful, non-linear, and difficult, and because the proton internal life is richer than any tidy first model can capture. Yet the mystery is not discouraging. It is productive. It has driven better experiments, sharper theory, and deeper computational tools, It has turned one familiar particle into a continuing source of insight about how nature builds matter. The proton does not sit at the end of explanation. It sits near the beginning of deeper explanation, where the visible world touches the complex hidden world of quarks, gluons, and confinement. And that leads quite naturally to the next question, because once we accept that protons and other hadrons are built from quarks and gluons in such a tightly bound and deeply mysterious way, we have to ask why quarks are never simply pulled out and displayed on their own, why the strong interaction refuses to let the building blocks appear in isolation, and why confinement remains one of the defining facts of the subatomic world. That refusal to let quarks appear on their own is not a side detail. It is one of the deepest facts about the strong interaction, and one of the main reasons hadrons are such unusual objects. If quarks behaved the way ordinary intuition expects, then a proton would be like a small assembly you could in principle pull apart piece by piece. It might be difficult, perhaps requiring a great deal of energy and some very determined laboratory equipment, but the logic would be familiar. Pull hard enough, and the pieces come free. That is how most composite things work in ordinary life. Tear apart a loaf, and you get crumbs. Smash a watch, and you get gears, springs, and a stern reminder that the warranty no longer applies. Break apart a molecule, and you get atoms. Break apart many nuclei, and you can sometimes identify protons and neutrons. So it would be natural to assume that if protons are made of quarks, then at some sufficiently energetic point, one ought to be able to break a proton open and simply extract its constituent quarks one by one. Nature does not allow that. This is the phenomenon called confinement, and it means that quarks are never found alone under ordinary conditions. They are permanently bound into hadrons. You can disturb a proton. You can smash hadrons together at extraordinary speeds. You can probe them deeply enough to reveal their internal structure. You can infer quarks from the way particles scatter, from the pattern of hadrons produced in high-energy collisions, and from the mathematical success of the theory that describes them. But you do not reach into a proton and pull out one free-up quark, set it on a table, and inspect its fractional charge at leisure. The strong interaction refuses to cooperate with that kind of demonstration. At first glance, that sounds almost unfair. Science likes observable things. It likes repeatable measurements and objects that can be prepared, manipulated, and studied directly. Quarks are undeniably central to modern particle physics, yet they are hidden in a peculiar way. We see their consequences everywhere inside hadrons, but we do not catch them wandering independently through ordinary matter. That made some physicists cautious in the early days of the quark model. It was one thing to propose quarks as mathematical constituents that explain the hadron families. It was another to claim full physical reality for objects that never seemed to show up on their own. What settled the issue was not one dramatic photograph of a lonely quark caught on a bad day. It was the steady accumulation of evidence that hadrons behave as though they contain point-like constituents, with exactly the kinds of properties the quark model and quantum chromodynamics require. The theory became too successful, the patterns too consistent, the scattering results too persuasive. Quarks were not dispensable bookkeeping devices, they were the hidden building blocks of hadrons. But they came with a rule. Unlike almost anything in ordinary experience, they remain confined. To understand why, it helps to revisit what makes the strong interaction so unusual. Quarks carry color charge, and gluons mediate the force associated with that charge. Unlike the carriers of electromagnetism in the simplest picture, gluons themselves carry the charge relevant to the force they transmit. That means the strong interaction is self-interacting in a way electromagnetism is not. The result is a field structure of extraordinary richness, one in which the force does not simply fade into irrelevance as quarks are separated. In fact, the opposite trend becomes crucial. At very short distances, quarks can behave as though they are less tightly constrained. This is the feature called asymptotic freedom. It means that if quarks are extremely close together, and the relevant energy scale is very high, the effective strength of the interaction becomes weaker in a certain technical sense. That is why high-energy scattering experiments can reveal point-like quark behavior inside hadrons. The quarks, under those conditions, look almost like independent constituents. But as soon as one tries to separate them over larger distances, the situation changes. The field linking the quarks does not politely spread out and weaken the way the electric field of isolated charges does. Instead, it tends to remain concentrated. A common image is that of a flux tube or a stretched string between quarks. The farther you try to pull them apart, the more energy is stored in that connection. So instead of becoming easier to separate with increasing distance, the system becomes more costly to stretch. That is the heart of confinement. Pulling quarks apart does not uncover freedom. It loads energy into the strong interaction field, and if you keep going, the system reaches a point where it is energetically favourable not to continue stretching the connection forever, but to produce new quark-antiquark pairs from the energy you have supplied. Once that happens, the original quarks do not emerge as isolated free particles. Instead, the system rearranges itself into new colour-neutral hadrons. This is such an important point that it is worth stating slowly. If you try to separate quarks, you do not usually get one quark on one side and one quark on the other. You get more hadrons. The strong interaction would rather turn your added energy into additional bound particles than surrender a single free quark. It is as though every attempt to pry open the proton simply convinces nature to build more hadrons in self-defense. That behavior is profoundly unlike our normal mechanical picture of a composite object. It means hadrons are not assemblies whose constituents merely happen to be stuck together. They are the only ordinary form in which quarks are allowed to exist. Quarks are not hidden inside hadrons by accident, and hadrons are not temporary storage boxes. Hadrons are the natural confined states produced by the strong interaction. In a very real sense, if you are looking for where quarks live, the answer is not inside hadrons, as though hadrons were separate from the issue. The answer is that hadrons are what quarks become when the strong interaction is allowed to do what it does. This explains why no one ever finds fractional electric charges drifting about in macroscopic life. Up quarks carry a positive charge of 2/3 of the proton charge. Down quarks carry a negative charge of 1/3. If free quarks existed under ordinary conditions, the world might contain isolated particles with these strange fractional charges. Experiments have searched for such things with great care, and none have been found in the way one would expect if free quarks were roaming about. Matter presents itself in whole electric charge units, because quarks are confined into combinations whose total charges come out as familiar integers. That is one of the quiet triumphs of the theory. It explains both the internal fractional charges and the external whole charges at once. Quarks are allowed to have their peculiar 1/3 and 2/3 values precisely because they are never found alone. Nature never needs to hand us a free 1/3 charged object in daily life. The quarks remain bound inside hadrons, where their charges add up to the ordinary values we observe directly in protons, neutrons, and mesons. There is another layer to confinement that makes it more than just an empirical rule. It is not simply that no one has yet managed to isolate a quark despite a century of trying. It is that the theory itself strongly suggests such isolation is not part of the allowed low-energy world. Quantum chromodynamics describes a universe in which colour-charged objects do not appear freely over ordinary distances. Only colour-neutral combinations are observed as stable particles. That is why baryons combine 3 quarks in a colour-neutral way, and mesons combine a quark and an antiquark in a colour-neutral way. The hadrons we observe are the permitted visible forms of colour-neutral matter under the strong interaction. This can feel abstract at first, but it has a practical experimental face. When very energetic collisions occur, such as those in particle accelerators, the quarks and gluons involved can be struck hard enough to behave briefly like nearly free constituents during the interaction itself. Yet even then, when the event settles, and the products move outward into the detector, one does not see naked quarks arriving. Instead, one sees sprays of hadrons, often called jets. These jets are the visible traces left by energetic quarks or gluons that have undergone hadronization, the process by which colour-charged partons turn into observable colour neutral hadrons. That word hadronization is important because it tells us how confinement expresses itself in violent experiments. High-energy collisions do reach into the quark and gluon world. They do disturb hadrons deeply. They do knock loose energetic partons in the language of the theory. But as those partons move outward, the strong interaction once again asserts its rules. Free colour charge does not remain free. The outgoing partons trigger the formation of new quark-antiquark pairs, and the energy is converted into showers of hadrons. The detector records not single quarks, but structured sprays of ordinary strongly interacting particles. This is why jets became such important evidence for the quark picture. They showed that something quark-like and gluon-like was happening inside the collision, even though the final observed particles were still hadrons. Confinement did not hide the quark world completely. It forced us to infer it through patterns rather than through isolation. In some ways, that made the science harder. In other ways, it made the evidence more satisfying, because the theory had to explain not only the existence of hadrons, but also the way energetic internal constituents reassemble themselves into hadronic final states. There is an intuitive trap here that is worth avoiding. Confinement does not mean quarks are somehow unreal or purely mathematical, quite the opposite. It means they are so deeply bound by the strong interaction that their reality is expressed through hadronic structure and collision patterns rather than through independent existence. A person might say, if quarks cannot be seen alone, how do we know they are really there? The answer is the same general answer science gives in many difficult cases. We know because the best theory describing a huge range of observations includes them as essential ingredients, and because the observed world behaves in ways that fit that theory with remarkable success. There is another useful comparison with the nuclear force. Protons and neutrons themselves can be bound inside nuclei, yet they can also be removed from nuclei under the right conditions. That might tempt someone to think quark confinement should work the same way if only we hit hard enough. But the analogy fails because the force binding nucleons in nuclei is a residual effect of the deeper strong interaction, not the full-colour confining mechanism at the quark level. Nucleons inside nuclei are not confined in the same absolute sense. Quarks inside nucleons are. A nucleus can be broken into protons and neutrons. A proton cannot, under ordinary conditions, be broken into a neat tray of free quarks. That difference is one of the clearest signs that hadrons are not just one more layer of ordinary assembly. They belong to a deeper regime where the basic charges and forces behave differently from the ones that structure atoms and chemistry. It is not just that quarks are smaller pieces than protons. It is that the rules governing quarks are unlike the rules that govern familiar composite systems. And yet confinement is not total silence. The quark world can be approached in extreme conditions. In the very hot, dense environment of the early universe, and in certain high-energy heavy ion collisions today, matter can enter a state known as quark-gluon plasma. In that state, quarks and gluons are no longer confined into individual hadrons in the ordinary way. This does not mean one gets tidy free quarks strolling about with name tags, but it does mean the strongly interacting matter exists in a different phase, where hadrons melt into a collective quark-gluon medium. That is a fascinating exception because it shows confinement is a property of the ordinary low-temperature hadronic phase, not an eternal law forbidding all other possibilities in every conceivable environment. The early universe, for example, was once so hot that hadrons as we know them could not yet exist stably. As the universe expanded and cooled, confinement set in and quarks became locked into hadrons. So the world of protons and neutrons is not just a matter of particles happening to exist. It is also a matter of cosmic conditions allowing the strong interaction to organize quarks into confined bound states. Still, in the world around us now, confinement rules the day. It is why matter is built from hadrons rather than from free quarks. It is why the proton can serve as one stable load-bearing particle of ordinary reality. It is why the fractional charges of quarks do not show up as isolated objects on your kitchen table or in your cutlery drawer, which would admittedly make breakfast considerably more exciting but much less predictable. Confinement also teaches something broader about how nature hides its foundations. We often imagine deeper layers of reality as being revealed simply by smashing things into smaller and smaller pieces until the final ingredients lie exposed. Sometimes that works, sometimes it fails in a more interesting way. At the hadronic level, smashing does not simply uncover independent constituents, it creates new bound states. The path to understanding becomes indirect. We infer the hidden pieces through their effects, their symmetries, their scattering behaviour, and the pattern of what emerges after violent interactions. Nature gives up the secret, but not in the form we first expected. That is one reason particle physics required such careful experimental design. You cannot understand quarks merely by hoping they will wander into view. You have to interrogate hadrons with high-energy probes, study the distributions of outgoing particles, and compare those results with theoretical predictions. You have to learn to read confinement not as the absence of information, but as a particular way information is encoded. The quarks are there. Their traces are there. Their momentum distributions are there. Their role in the structure of hadrons is there. But they remain hidden behind the rule that colour-charged objects do not emerge alone. There is also something aesthetically satisfying about confinement, even if it can be maddening in calculation. It ties together several otherwise peculiar facts into one coherent picture. Why are hadrons the observed strongly interacting particles? Because quarks are confined into colour-neutral combinations. Why do quarks carry fractional charge without ever appearing alone? Because confinement keeps them in hadrons. Why do high-energy collisions produce jets of hadrons rather than isolated quarks? Because energetic quarks and gluons hadronize. Why is the proton a stable composite object rather than a loose assembly of smaller visible charges? Because the strong interaction does not permit free quark constituents. The theory that captures this, quantum chromodynamics, is one of the most successful and demanding parts of modern physics. It explains asymptotic freedom at very short distances and confinement at the scales of ordinary hadrons. That pair of features is especially striking. The same theory says that quarks can look almost free when probed very closely, yet can never escape into freedom at larger distances. The deeper you look, the more point-like they seem. The harder you try to separate them, the more firmly the theory binds them into hadrons. It is an arrangement almost designed to challenge the expectations of anyone raised on springs, magnets, and manageable household objects, and perhaps that is why confinement remains such a memorable idea once it is understood. It is not just a technical feature, it is a reminder that the deepest building blocks are not always available as isolated pieces. Sometimes the basic ingredients of a theory only exist physically inside larger wholes. Sometimes the most elementary things are hidden not because they are unimportant, but because the laws of nature insist on presenting them only in collective form. Quarks are fundamental, but the world shows them to us through hadrons. By this point then, the proton has become far more than the familiar positive particle from elementary atomic diagrams. It is a confined, strongly bound, dynamically rich object built from quarks and gluons that cannot be separated in any ordinary sense. Its constituents are real, but their reality is inseparable from the hadronic states in which they live. The proton is not hiding simpler pieces like a pocket full of coins. It is the stable visible face of confinement itself, and that naturally leads to the next step, because if confinement refuses to let us pull hadrons apart neatly, then the only way to learn what they are hiding is to hit them hard enough that their internal structure reveals itself indirectly in the wreckage, which is exactly what particle physicists learned to do when they began smashing hadrons together to see what secrets they were keeping. That is exactly what physicists learned to do, because once confinement made it clear that quarks would not present themselves politely on their own, there was really only one option left. If you cannot take a hadron apart neatly, and lay the pieces on a tray, you have to probe it hard enough that its internal structure reveals itself indirectly. You ask violent questions and then study the answers with extreme care. This is one of the reasons particle physics can sound so contradictory from the outside. It deals in incredibly small things, yet the machinery involved is enormous. It studies the quiet foundations of matter by means of thunderous collisions. It wants to know what is hidden inside a proton, so it builds accelerators that send particles hurtling around underground rings at astonishing speeds, and then watches what happens when they crash. There is something both elegant and slightly unreasonable about that method, but it works. The basic idea of a scattering experiment is simple enough in spirit. If you want to know what an object is like inside, you send something into it and observe how the probe bounces, deflects, or breaks it apart. Light reveals surfaces, sound reveals echoes. Medical imaging uses carefully controlled probes to show hidden structures inside the body. At subatomic scales, physicists do something conceptually similar, though with rather more mathematics and considerably less soothing bedside language. They fire particles at targets and read the results. The pattern of deflection, energy transfer and debris carries information about what lies within. This approach had already transformed the understanding of the atom long before the proton became the main focus. It was by scattering particles off thin metal foils that physicists discovered the atomic nucleus in the first place. Most of the incoming particles passed through with little disturbance, but a few were deflected sharply, revealing that the positive charge and most of the mass of the atom were concentrated in a tiny central region. That was one of the great shocks of early modern physics. Matter, which felt solid and continuous, turned out to contain a surprising amount of emptiness. Later, the same logic was pushed deeper. If nuclei could be probed, then protons and neutrons could be probed too, and if they were not truly elementary, then perhaps sufficiently energetic collisions would reveal that fact. But here there was an immediate problem. To see very small structures, you need very short wavelengths, or very high momentum probes. In other words, you need more energetic particles. Looking more closely at nature is not just a matter of better microscopes. At some scale, it becomes a matter of greater violence. That is one of the more unsettling administrative decisions made by the universe. So physicists built accelerators. An accelerator, at heart, is a machine for taking charged particles and giving them enormous energy. Electric fields push them forward. Magnetic fields steer them into controlled paths. The particles are sped up to extraordinary velocities, guided into beams, and either sent into fixed targets or collided head-on with other beams. Every part of this process has to be managed with absurd precision. A particle beam is not a casual spray. It is a tightly controlled stream of subatomic projectiles moving with such energy that when collisions happen, they recreate conditions far more extreme than anything found in ordinary matter. There are different ways to do this, and each tells us something different. In a fixed target experiment, one beam is fired into a stationary sample. In a collider, two beams are accelerated in opposite directions and brought into collision. The collider approach is especially powerful because more of the energy is available for the interaction itself rather than being wasted in the motion of the combined system. That made colliders a crucial tool in modern particle physics, especially when the questions involve the deep internal structure of hadrons. Now, when people hear that physicists smash hadrons together, there is often an understandable mental image of tiny objects exploding, like crockery dropped from a great height. That image is not entirely useless, but it is far too crude. A hadron collision is not just an impact between two hard little balls. It is an interaction between complex quantum systems made of quarks and gluons. In many cases, the most relevant collision is not even between the protons as whole objects. It is between individual partons inside them, quarks or gluons carrying some fraction of the proton total momentum. So the event is not one simple crash. It is a structured encounter between internal constituents governed by the strong interaction and the electro-weak forces. This is why high-energy hadron collisions are both so powerful and so difficult to interpret. On the one hand, protons are easy to accelerate, stable, and abundant. They are excellent projectiles for reaching enormous energies. On the other hand, they are messy projectiles because each proton is itself a composite system. When two protons collide, you are not colliding two clean elementary points. You are colliding two crowded hadrons full of quarks, gluons, and a restless internal sea. It is less like crashing two billiard balls and more like colliding two swarms whose internal members can interact in multiple different ways. Yet that very messiness is also what makes proton collisions so informative. Because the proton contains quarks and gluons, the collision products can reveal how those constituents behave. If you study enough events, and if your detectors are precise enough, and if your theory is disciplined enough not to panic, then patterns emerge. Those patterns tell you about the momentum distributions of quarks and gluons, the presence of C-quarks, the role of gluons in carrying proton momentum, and the way confined constituents manifest themselves in the final states. One of the decisive breakthroughs in this story came from deep, inelastic scattering. The name is not especially charming, but the physics behind it is magnificent. In these experiments, very energetic electrons were fired at protons. Electrons were especially useful because they do not feel the strong interaction in the same way hadrons do, so they serve as relatively clean probes of the proton internal structure. When the electron struck the proton hard enough, the scattering pattern revealed that the proton did not behave like a smooth, structureless object. Instead, it behaved as though it contained smaller point-like constituents carrying momentum inside it. That was a turning point. It showed that the proton had internal structure of exactly the kind one would expect if quarks, or something very much like quarks, were real constituents. The results were not consistent with the old picture of the proton as a featureless bead. They pointed to localized internal objects. In time, these objects were understood in the broader language of partons, the momentum-carrying constituents inside hadrons, which at high energies correspond to quarks and gluons in the underlying theory. There is a quiet beauty in that method. Because confinement prevents us from isolating quarks directly, physicists learned to interrogate the proton by hitting it with electrons and reading the way the proton answered. The proton could not be opened neatly, but it could be made to reveal that it was not smooth inside. Its interior had granularity, organization, and active constituents. The hadron was telling us its secret, not by surrendering free quarks, but by scattering in a way only a structured object could. As accelerators improved, the game became even more ambitious. It was no longer enough to know that hadrons contained point-like constituents. Physicists wanted to know how many, what kinds, how their momentum was distributed, how gluons contributed, how C-quarks appeared, and what new particles might be created when hadrons were smashed together with enough energy. Because once you collide hadrons at very high energies, you do not merely probe what is inside. You can also convert collision energy into entirely new particles. That follows from one of the most consequential facts in all of physics. Energy can appear as mass in the creation of new particles, provided the conservation laws are respected and the conditions are sufficient. So a hadron collider is not only a microscope. It is also a forge. It can reveal internal structure and produce new forms of matter in the same machine. That dual role is part of what makes colliders so central to modern physics. They let us look inward and outward at once, downward into structure, and forward into possibility. When protons collide at very high energies, the actual interaction may involve quarks smashing into quarks, quarks interacting with gluons, or gluons interacting with one another. Because gluons are so abundant inside fast-moving protons, especially at certain momentum scales, many important events in modern proton colliders involve gluons in essential ways. This is another reminder that the proton is not simply three valence quarks doing all the public-facing work. The gluon content matters enormously in real collisions. What emerges from these interactions is not a neat little pile of exposed quarks. Confinement still applies. Instead, the energetic outgoing quarks and gluons undergo hadronization. They produce sprays of hadrons moving in roughly aligned directions known as jets. A jet is one of the most important signatures in high-energy particle physics. It is the visible aftermath of a quark or gluon that cannot remain free and therefore turns its energy into a stream of hadrons. So when detectors see jets, they are often seeing the indirect trace of quarks and gluons that briefly participated in the collision as nearly free partons before confinement reasserted itself. This is one of those ideas that is almost too clever to be true, except that experiments confirm it in extraordinary detail. Physicists do not see a free quark arrive in the detector. They see a jet, and from the shape, energy, direction, and structure of that jet, they infer the underlying partonic process. Nature does not hand over the building blocks one by one. It leaves patterns in the wreckage, and physics learns to read them. Reading that wreckage is the job of detectors, and detectors are wonders in their own right. A modern particle detector is not one device, but a layered system, designed to measure different properties of the particles produced in collisions. There are inner tracking systems that record the paths of charged particles as they curve in magnetic fields. There are calorimeters that absorb particles and measure their energy. There are outer systems designed to identify penetrating particles such as muons. Each layer contributes a different piece of the event. The goal is to reconstruct what happened at the collision point from the traces left behind. The amount of information involved is enormous. In a busy hadron collision, many particles can emerge at once. Some are long-lived enough to travel measurable distances. Some decay almost immediately into lighter products. Some carry charge and leave curved tracks. Some are neutral and announce themselves only through deposited energy. Some escape detection directly and must be inferred from missing momentum in the event. The detector does not produce a tiny photograph of the proton interior. It produces data, and from that data, physicists reconstruct the logic of what occurred. That reconstruction is one of the most demanding forms of scientific interpretation anywhere. It requires theoretical models, simulation tools, calibration studies, statistical methods, and a near-heroic tolerance for complexity. But it also allows extraordinary discoveries. It is how physics confirmed the existence of many predicted particles, studied the detailed structure of hadrons, and eventually discovered the Higgs boson in proton collisions. All of that came, in one way or another, from learning how to smash hadrons and make sense of the aftermath. There is a wonderful irony in using protons, which are composite and messy, to search for the deepest truths of particle physics. One might think cleaner projectiles would always be preferable, and in some contexts they are. Electron-positron colliders, for example, provide extremely clean collision environments because electrons and positrons are elementary particles rather than hadrons. But proton colliders have one overwhelming advantage. They can reach enormous energies. Because protons are heavier and easier to accelerate without losing so much energy to certain effects, they are superb tools for pushing into new energy territory. So even though they are messy, they are also mighty. That is why machines like the Large Hadron Collider became so important. They are not just smashing protons for spectacle, although the scale of the enterprise does have a certain theatrical flair. They are using proton collisions to explore the energy frontier, to produce rare processes, and to test the deep structure of the standard model of particle physics. In every such collision, the proton internal constituents, the quarks and gluons, are the true participants, and the patterns of what emerges tell us about both the known structure of hadrons and the possibility of new physics beyond what is already established. Still, for our purposes tonight, the most important point is not any single machine or discovery, but the principle itself. Smashing hadrons became necessary, because confinement forbids simpler methods. You cannot unscrew a proton. You cannot pour out its quarks. You cannot hold a gluon in tweezers and ask it what it has been up to inside the hadron. You have to collide, measure, infer, and reconstruct. You have to ask the proton what it is hiding by forcing it into conditions where its internal structure matters visibly. And the proton has answered again and again, though never in a simple voice. It answered by revealing point-like constituents in deep, inelastic scattering. It answered by producing jets consistent with quarks and gluons. It answered by showing that gluons carry a large fraction of proton momentum. It answered by making clear that the sea of quark-antiquark pairs is not an optional embellishment, but part of the real internal structure. It answered by turning hadron collisions into a laboratory for studying both the proton itself and the wider particle world. And every answer carried the same basic lesson. The proton is not elementary. It is a hadron, and what it hides is not a neat collection of tiny objects but a dynamic quantum system governed by the strong interaction. There is also something almost touching in the persistence this demanded from science. The proton did not volunteer its inner life. Physicists had to build larger accelerators, better detectors, sharper theories, and more powerful computational tools decade after decade. The project required international collaborations, colossal engineering, and an astonishing willingness to spend years refining the interpretation of a signal that lasts less than a heartbeat. All that labour in part so we could understand what is going on inside one of the most ordinary particles in the universe. If that does not count as devotion to the truth, I am not sure what does. And yet the effort was worth it, because the proton turned out to be a gateway to a deeper understanding of matter itself. By smashing hadrons and reading the aftermath, physicists learned not only what hadrons are made of, but how the strong interaction behaves, how confinement works in practice, how mass emerges in ordinary matter, and how even the most familiar particles can conceal extraordinary internal richness. The proton, once thought simple, became a laboratory of hidden structure. There is one further twist here, and it is an important one. The more powerful our collisions become, the more they reveal that hadrons are not limited to the familiar protons, neutrons, and simple mesons of early models. The strong interaction appears able to organize quarks into more exotic combinations as well, and those possibilities began to emerge more clearly once experiments became capable of seeing beyond the conventional hadron families. Which means that after smashing hadrons to discover what protons were hiding, physicists found themselves facing an even more intriguing question about what other kinds of hadrons nature might be willing to build. By the time physicists had learned to read proton collisions, study jets, trace patterns, and map the crowded interior of hadrons, one comforting idea still remained in the background. Perhaps, people thought, the proton and neutron were complicated, yes, and mesons were real enough, yes, but at least the strong interaction probably arranged quarks into only a few standard patterns. 3 quarks for baryons, 1 quark and 1 antiquark for mesons. A slightly untidy family perhaps, but manageable. A household with rules. You could imagine the strong interaction as a very strict host, allowing only certain seating arrangements and asking everyone else to leave. And then nature, with its usual timing, gave us reasons to suspect that the guest list was longer. This is where exotic hadrons enter the story, and they matter for more than just the pleasure of discovering new particle names. They matter because they force us to think more carefully about what a hadron really is. If the proton first taught physicists that apparently simple particles could hide a rich internal world, exotic hadrons taught them that even the accepted categories of that world might not be the whole story. The strong interaction may be willing to build more than the familiar textbook combinations. And if that is true, then hadrons are not just old known particles with a few well-behaved relatives. They are evidence that matter, even at this deep level, has more structural possibilities than we first expected. To understand why that is such a big deal, it helps to remember what the ordinary picture looked like. For a long time, the simple quark model organized hadrons very effectively. Baryons were built from 3 quarks, mesons were built from 1 quark and 1 antiquark. This scheme explained a great deal. It brought order to the hadron zoo. It accounted for many observed particle families. It connected beautifully with the deeper theory of the strong interaction. There was no reason to throw it out because it worked, and it still works remarkably well for an enormous part of hadron physics. But successful models are not always complete models. Sometimes they capture the dominant cases while leaving room for states that are rarer, subtler, or harder to identify. Quantum chromodynamics, the deeper theory describing quarks and gluons, does not obviously stop at only the simplest possible bound arrangements. If quarks are confined by the strong interaction into color-neutral combinations, then in principle, more complicated combinations may be possible, provided the color charges cancel appropriately and the resulting state is dynamically allowed. The theory itself is richer than the earliest tidy summary of it. That is what makes the word exotic so interesting here. It does not mean fictional, and it does not mean forbidden. It means a hadron whose internal quark arrangement goes beyond the simplest conventional categories of 3 quarks for baryons and 1 quark with 1 antiquark for mesons. The best known examples are tetraquarks, which involve 4 quark constituents in an overall color-neutral state, and pentaquarks, which involve 5. There are also long-standing discussions about other possibilities, including states in which gluons play a more explicit structural role than usual, sometimes called glue balls, though those are notoriously difficult to identify cleanly because hadrons have a habit of mixing, overlapping, and generally refusing to wear labels where experimentalists would most appreciate them. At first, the idea of exotic hadrons could sound like a kind of optional complication, the particle physics equivalent of finding out that the menu has seasonal specials after one has only just memorized the regular dishes. But they go much deeper than that. They test whether our picture of hadron formation is truly general. They test how the strong interaction organizes quarks into stable or short-lived bound states. They ask whether the distinction between ordinary hadrons and more complicated ones is fundamental or merely historical. In that sense, exotic hadrons are not a sideshow. They are probes of the logic of confinement itself. One important thing to say right away is that none of this means the proton stops being what it is. Exotic hadrons do not overturn the reality of protons, neutrons, or ordinary mesons. They do not announce that everything we knew was wrong. Quite the opposite. They emerge from the same deeper theory that already explains ordinary hadron so well. What they show is that the strong interaction may admit a broader range of bound states than the simplest early model emphasized. The furniture of matter remains the same. We have simply learned that the workshop producing that furniture may be capable of stranger designs than initially advertised. Part of the challenge in identifying exotic hadrons is that the strong interaction does not present these states in an easy-to-catalogue way. Hadrons are not little tagged objects waiting in orderly rows. Many of them are unstable and decay rapidly. Some overlap in mass and quantum properties. Some can mimic one another in decay channels. Some may be more like loosely bound hadronic molecules, states made from 2 hadrons weakly associated with each other, rather than tightly bound multiquark objects in the most compact sense. And some may not fit neatly into either picture. That makes the whole field experimentally rich and occasionally maddening. Still, over the past decades, evidence has accumulated for states that are difficult to explain as ordinary baryons or mesons alone. Some observed particles appear to behave like tetraquark candidates. Others resemble pentaquark candidates. Their masses, decay patterns, and production behavior suggest that something beyond the simplest conventional hadron categories is going on. Even when debate remains over the exact internal interpretation, the broader lesson is clear. The strong interaction is capable of building more varied structures than a first pass through the quark model might imply. This matters because it sharpens a question that has been hovering over the entire discussion from the beginning. What is a hadron really? Is it best thought of as a fixed set of conventional constituent patterns, or more generally as any color-neutral bound state arising from quarks and gluons under the strong interaction? Once exotic candidates appear, the second view becomes harder to avoid. The hadron is not merely a proton, neutron, or familiar meson. It is a category defined by the logic of confinement and colour neutrality. That category may include ordinary members and unusual members, stable residents and fleeting visitors, but the underlying principle is the same. There is a useful analogy with chemistry, though as always one should not lean on such comparisons too hard. Early chemistry might first identify a set of common molecules and think those are the main forms matter takes. Later, with better tools and wider conditions, it discovers more elaborate compounds, unstable intermediates, unusual rings, odd coordination states, and a whole wider landscape of possibilities. The existence of more exotic compounds does not invalidate water or salt. It reveals that the underlying bonding rules permit a broader chemistry than first appreciated. Something similar has happened with hadrons. The proton remains real and central. The neutron remains real and central. But the strong interaction may have a broader hadronic chemistry than the earliest tidy picture suggested. Another reason exotic hadrons matter is that they force theorists to refine their language about constituent quarks. In the simple quark model, one can speak rather comfortably about baryons and mesons as though the constituent count were the essential whole story. But once tetraquark and pentaquark states enter the frame, the role of gluons, C-quarks, correlations and dynamical clustering becomes more prominent. Are the quarks grouped as compact multiquark states? Are they better described as paired substructures? Are some candidates effectively hadronic molecules, held together in a looser way by residual strong forces rather than by a single tightly compact core? These are not trivial distinctions. They affect how we understand hadron formation and what kinds of structures quantum chromodynamics naturally favours. That question of compactness is especially interesting. A tetraquark, for example, might be imagined as 4 quarks crowded into one tight-bound state. But some candidates may be better thought of as 2 meson-like units in a looser association, more analogous in spirit to a molecule than to a single compact nucleus. In both cases, the final state is exotic relative to the old simple categories, but the internal dynamics differ. This is why identifying a new hadron candidate is only the beginning. The harder task is figuring out what sort of hadron it actually is, and the strong interaction, consistent as ever in its refusal to make things too easy, allows these possibilities to blur into one another. Bound states near threshold can be especially delicate. A resonance may look at first like one thing and later be interpreted another way. Experimental groups may measure masses and widths with increasing precision while theorists debate whether the signal fits a compact tetraquark, a hadronic molecule, or something in between. This is not a sign of confusion in the lazy sense. It is what happens when one studies a genuinely complicated theory in a regime where multiple structures are possible and the data must be interpreted with care. There is also the intriguing possibility of glue balls, hadronic states built primarily from gluons rather than from valence quarks in the usual way. Since gluons carry colour charge and interact with one another, quantum chromodynamics appears to allow the possibility that gluons might bind into colour-neutral states of their own. If such objects exist cleanly, they would be a remarkable confirmation that the strong force carriers are not merely holding quarks together, but can in some sense become hadronic matter themselves. Yet identifying a pure glue ball in practice is difficult because real hadronic states can mix. The strong interaction is not obliged to separate its ingredients into neat independent categories for our convenience. Even that difficulty teaches us something. It reminds us that hadrons are not little mechanical kits, with unambiguous parts arranged visibly in fixed slots. They are quantum states. Their identities can overlap, mix, and depend on the dynamics of the full theory. The deeper story of matter is not one of final tiny bricks stacked in perfect isolation. It is one of allowed structures emerging from fields, interactions, and symmetries. Exotic hadrons make that point more forcefully than almost anything else in the subject. They also tell us something about the limits of our intuition. The word exotic can tempt the mind to imagine bizarre objects wildly unlike ordinary hadrons, perhaps glowing faintly in a morally concerning way. In truth, the exoticity is often quite technical. These are still hadrons. They are still bound states arising from the strong interaction. They still obey conservation laws. They still appear in detectors as resonances, decay products, and patterns in scattering data. The difference is not that they are supernatural. The difference is that their internal composition stretches the conventional categories and forces us to ask what combinations the theory truly allows. In that way, exotic hadrons are a healthy corrective to the tendency to mistake the first successful model for the final ontological map. Science often begins with the most stable, abundant, or easy to classify examples. It then gradually discovers edge cases, rare structures and conditions under which the old categories no longer feel complete. The proton was once thought elementary. Then it became a 3-quark hadron. Then it became a dynamically rich system of valence quarks, gluons and C-quarks. Now the very notion of what kinds of hadrons can exist has broadened beyond the simplest early picture. At every step, matter remained real. The picture simply deepened. There is also a subtle philosophical point hiding here, though it deserves to be stated plainly rather than dressed up too much. Matter is not simple just because it is familiar. The visible world appears stable and ordinary because the underlying forces build stable structures reliably. But reliability should not be confused with simplicity. The proton is reliable. The neutron is reliable inside nuclei under the right conditions. Ordinary atoms are reliable enough that architecture, metabolism, and breakfast all continue functioning most days. Yet beneath that reliability lies a strong interaction, capable of far more varied and intricate structures than human intuition would ever have guessed without experiment. That, in a way, is the deeper story of matter. Matter is not merely what sits there. Matter is what the laws of nature permit to persist. Some forms are stable enough to build stars and chemistry. Some are brief and visible only in colliders. Some are conventional enough to appear in every textbook. Some are exotic enough to require decades of careful analysis before the community agrees on what has been seen. But all of them belong to one broader narrative. The world is built not from simple little solids alone, but from bound states, emergent properties, field dynamics, and the deep organizing force of quantum chromodynamics. And if one steps back far enough, the story becomes almost cosmological. In the early universe, before hadrons formed in the way we know them now, quarks and gluons existed in a different state of matter, hot and dense beyond ordinary imagination. As the universe cooled, confinement set in and hadrons emerged. Protons and neutrons became possible. Nuclei eventually formed. Atoms later formed. Stars ignited. Heavier elements were forged. Chemistry took shape. Planets condensed. Biology happened. Listeners found themselves lying awake with one eyebrow slightly raised, at the thought that the whole visible world depends so heavily on a force that keeps quarks forever confined, while occasionally allowing them to arrange themselves into particles with names like strange mesons and pentaquarks. It is a long chain of consequences, but it is the right one. What exotic hadrons add to that cosmic story is a reminder that matter is not exhausted by the most common arrangements. The universe contains ordinary and less ordinary possibilities. Some bound states become the durable framework of daily existence. Others flash into being only under energetic conditions and vanish almost immediately. Yet even those short-lived states matter scientifically because they reveal what the theory permits. They show us the full expressive range of the strong interaction, not just its most domesticated products. There is something quietly beautiful in that. The same force that gives us the proton, and through the proton, the stable architecture of visible matter also allows more unusual hadronic states to appear under the right conditions. The laws do not merely produce one favoured particle and stop. They generate a landscape. Some parts of that landscape are familiar terrain, some are steep, fleeting and harder to map, but it is one landscape all the same, and perhaps that is where this whole journey finally settles. We began with the deceptively simple question of what hadron really is, and along the way the answer kept growing. A hadron is not a tiny solid pebble, it is a bound state of quarks and gluons shaped by the strong interaction. A proton is not just 3 quarks, it is a dynamically rich system with gluons, quarks, emergent mass, shared spin, and confinement at its core. Matter is not built from final neat grains alone. It is built from organised interactions that generate stable wholes. And exotic hadrons remind us that even this deep layer of matter still has room for surprise. So the deeper story of matter is not that the universe hides a final little collection of hard beads and then goes quiet. It is that the universe builds structure through rules, through binding, through energy, through confinement, and through possibilities that only reveal themselves when we ask better questions. The proton is one answer, the neutron is another, mesons are others. Exotic hadrons widen the answer still further. And all of them together tell us that the ordinary world, the solid and sensible world of tables, bones, rain, dust and starlight, rests on a hidden subatomic life far more active and inventive than it first appears.